Okay, let's get started. So we're in the seventh episode of our measure theory series, and I just renamed the series to Measure Theory and Rigorous Probability. So in the first of 6 episodes, we introduced why measure theory is needed, the notion of sigma algebra, outer measure, as well as measurable functions. And today we're going to finally define measures, and we will work towards constructing the Lebesgue measure. Okay. So this is in fact, in my opinion, perhaps the most difficult stage for a beginner, that is constructing the Lebesgue measure. Once you constructed the Lebesgue measure, defining the Lebesgue integral is relatively easy, relatively speaking, and you will see why we went to such trouble of defining measure, because as we shall see, the construction of a Lebesgue integral solves many of the fundamental issues that we have with Riemann integrals, which is the topic of the first chapter, episode 1. And in addition to that, starting from this series, I decided to split the streams in half. So for the first half, we're going to use Axler's book, the one we've been using. And the second, we'll use Professor Robert Ashe's book called Real Analysis and Probability. So there we will gradually introduce measure theoretic probability, as well as some functional analysis, basic functional analysis. So that's the plan anyway. We'll see how that goes. Hopefully it goes well. And so this is a book. Okay, so I'm just going to show you the book. This book is, unfortunately, is not available for free. So I'm just going to give you the name, Real Analysis and Probability, book by Robert Ashe. Professor Ashe was a fantastic writer, first published in 1972. So yeah, that's the book we will use concurrently, in addition to Axler's book, because a few months ago, I made a video called Measure Theory Made Doable, in which I recommended these two books. So the book by Axler, which is available for free, and this one is a physical book. If I recall correctly, it's actually quite expensive. That's unfortunate. On Amazon, it shows right now it's 128 Canadian dollars. So I will not show the book, but I will be as faithful as possible and do a lot of transcription as well as my own commentary. All right, so without further ado, let's just get started. This is going to be a long one. Okay, it's this one. Right now it's almost 7. Okay, almost 7. I initially decided to start at 7, but I figured, okay, well, what the heck, might as well just start now. And my plan for today is going to be 5 hours. So you feel free to stay as long as you can. I know, like, this is a big commitment. I don't ask everyone to stay for that long, but this is how I plan to study the thing, okay, or review mostly for me. But you know what? Every now and then, coming back to subjects that you've taken before in the university or whatnot, give you a much better understanding, because in the university, what you really care about, I mean, I wouldn't be as cynical as saying what you really care about is great, but there's definitely a lot of emphasis on speed, right? So sometimes you just focus on problem solving, get the practice problem done, without thinking too much, why we define things this way or that way, right? So we're trying to be as thorough as possible, because as I said before on the channel, our goal is really to get the subject in a way that it is almost as if we can develop it independently from scratch. Okay, the idea is not only we need to check the arguments of the proof, okay, which step comes from where, that sort of thing, but also think, how can we say construct such a proof? Okay, how can we discover the proof? Okay, why are the axioms stated this way, and that kind of thing. All right, so that's what we're getting at. Okay, so I figured, I said, oh, I'm gonna do 5 hours, and now immediately only 2 people are watching. That's fair enough. You know, this is a big time commitment. This is mathematics is a big time commitment of your life. Okay, if when someone tells you, oh, I'm gonna teach you maybe not measure theory but calculus in an hour, I don't know. Like, this is not something I can do. Okay, I think maybe I can explain the definition of limit in an hour, but perhaps not the whole calculus. But this is just how we do things on this channel. All right. So once again, questions are extremely welcome, and this is after all, as I said many times, it's not a lecture. This is not a lecture. It's just you can think of it as behind the scene of those more polished videos. So anyway, let's go back to the Axler. Okay, so now we're ready to define measures. So what are measures? 2C, section 2C, measures and their properties. Definition and examples of measures. The original motivation for the next definition came from trying to extend the notion of the length of an interval. However, the definition below allows us to discuss size in many more contexts. For example, we will see later that the area of a set in a plane or the volume of a set in higher dimensions fits into the structure. The word measure allows us to use a single word instead of repeating theorems for length, area, and volume. Yeah, I would like to mention that it's not just length, area, and volume, isn't it? Right? Also probability, and also math. Like in physics, mass and to define mass is a troublesome notion, by the way, and is a troublesome matter in physics, and also the notion of charge, like just how much stuff is contained in a set. That's the idea. To give a notion of a size to a set. That's basically what measure is. All right. So let's start with the definition, 2.5.4. So definition 2.54. So we're gonna. Oh, hi. Greetings from Canada. Thanks for joining the stream. So definition of measure. Suppose X is a set and S is a sigma algebra on X. Okay, so we're going to use the definition of sigma algebra here. Remember, what is a sigma algebra? A sigma algebra is a class of subsets of X that satisfies 3 properties. 1, S contains, not contains, but S includes big X. That is to say, big X is a member of scripted S, the sigma algebra. Second, we want S to be closed under complementation. That is to say, if a set A, which is a subset of X, is in scripted S, its complement is also in S. That's the second property. And the third property is called countable, closed under countable union. So if you have a sequence of subsets, say A1 all the way to AN and so on, it's a sequence, it's infinite, that means, that implies that the union of all of them is also in S. So that's the definition of sigma algebra. We did a few exercises in the past sessions. So now we now define what a measure is, all right? So a measure on this notation, okay, this notation we've seen that earlier. This is called a measurable space. A pair, X and scripted S together is called a measurable space. So a measurable space is a set equipped with a sigma algebra. A measure on a measurable space, XS, is a function mu that maps from the sigma algebra, scripted S, into the interval, a closed interval, 0 to infinity. So infinity is attainable here. So that means this interval is a subset of the extended real, not the ordinary real. Okay, so there you go. That's a function. So it takes a set in the sigma algebra, It is only defined over the sigma algebra. Remember why we do that? Well, that was the first section of chapter 2 on outer measure. An outer measure, because outer measure was defined over all subsets of R. The outer measure we attempted to give a notion of size to all subsets of R, and we selected a rather intuitive candidate called the outer measure. And the outer measure, unfortunately, suffers from some undesirable properties, which is the following. So here, mu is which is the following, namely countable additivity. Mu is designed specifically to remedy that problem by restricting the domain to be not all subsets, but rather the sigma algebra. So that's the whole reason why the measure is defined over sigma algebra. That is to avoid the undesirability of outer measure. And in fact, there is a stronger theorem that says there is no notion of size that extend the length, the ordinary length for intervals, that is defined on all subsets of R, as well as satisfy the desirable properties, things like the countable additivity, translational invariance, and no such thing. Okay, so that's why we're using the sigma algebra as a domain. Okay, and of course, sigma algebra over a set is not unique. The sigma algebra can be as trivial as just the empty set and big X, and it can be as large as the power set. But here, we are taking a sigma algebra as the domain, and typically S is between those two extreme scenarios. Okay, so it's typically between the trivial sigma algebra and the power set of X. So that's a function mu. So the measure is a function from the sigma algebra to a non-negative extended real, such that the empty set has a measure mu of 0. And the crucial property here, this is the one that we really wanted. Right? This is the one that turns out to be a crucial property that gives us a rich integration theory. That is to say, for a disjoint sequence E1, E2, and so on of sets in S, mu of their union, so this is a disjoint union. The measure of the disjoint union is the sum of the measure of individual sets, which is an infinite series in general. Okay, so basically that's the defining characteristic of measure. Okay, so the most important thing you need to remember is that measure is defined over the sigma algebra and it satisfies countable additivity. Okay, so why don't we just put that definition down in our notes. So Axler 2.54. So that was also a brief review of the main ideas we covered earlier. Okay. So S is a set. Oh, sorry, big X is a set. And sigma algebra. Hi, George Peng. I remember this series started because of your request. Okay, so we're gonna do this till the end. Okay, so S is a sigma algebra. Remember, S, this is a measurable space. This is a measurable space, and a measure. Okay, a measure is a function. Mu from scripted S to the semi-infinite interval, which can be infinite because, well, often big X has infinite length or infinite size, whatever you want to call it. Okay, so and it satisfies, and mu is That is okay. That is sorry. That is a countable additive. Countably additive. Remember, countable additivity always implies finite additivity. So this is a stronger condition than finite additivity. Mu of the union, k from 1 to infinity, ek, is the sum of mu of ek, where k goes from 1 to infinity, for every disjoint sequence. U is a function with s values and no solution. Let me explain that. Okay, so this does not seem to be a correct understanding, but let me just finish writing this sentence and I'll reiterate what we just defined. Okay, so this is a very formal definition. The fundamental idea is really just that you select a set and it tells you what size it is, such as the length, area, volume, like that. Okay, so mu, this function mu, assigns a set in the sigma algebra and non-negative extended real, and call that the size of mu. So that's essentially the what does it say? Okay, so yeah, this is a big X. This is a big X, all right. And let's suppose this is a set, say E, that's in the sigma algebra. So let's suppose E is in the sigma algebra. Then this function mu will tell you how big the set is. It gives you a number or infinity. Oh, hi Christian. Thank you very much for joining the stream. So yeah, that's the definition of measure. It just tells you how big a set is. And it has this property called countable additivity, and also it is defined over the sigma algebra. Okay, so that's why we spend all this time discussing sigma algebra, because that's literally the domain of measure. For sets that are not in the sigma algebra, we simply ignore them. Okay, we don't assign a measure to them. Okay, so that's it. Okay, so now it's time for some examples. Okay, so here first of all we have some comments. Mr. Repro, is that clear? Is the definition of measure now clear? Not with S values, right? So based on your writing, its values is in the extended real, non-negative extended real. It takes sets in scripted as input, not values, and not no solution for 0. If you use empty set, it still is a valid member in the sigma algebra. It's not no solution. It returns a valid response. So think of mu as a program. If you feed in the empty set into it, it would not return an error message. Instead, you just say that has size 0. Okay, an empty set always have a measure of 0, but a set of measure 0 don't have to be empty set. A lot of non-empty sets, in fact, a lot of infinite sets can have measure 0. Is it something like projection? No, not like projection either. I don't think it's a projection. It's a valid analogy. So projection is something like, for example, in linear algebra, a projection is a linear operator. Or in some textbook, you feed in a tuple, say x1 all the way to xn. The projection of the i's coordinate is just xi. So that's a projection. That's also a projection. But regardless, this has nothing to do with projection, orthogonality, none of those things. It's just a you can think of it as a black box, right? In high school, we learned that function can be treated as a black box. What does this black box do? You feed a set into it, a nice, quote-unquote, nice set to it, and it tells you its size. This is what it does. Yeah, Christian nailed it. A projection is a linear operator. So for that, you need a linear space. You need a vector space. Right? And the squares itself. So basically, if you project a same vector twice using the same projection. Right? So this is the idea. So it doesn't have to be orthogonal projection. Okay. Let's say, the projection of a vector is this. Okay, this is a vector v, and this is a projection of v onto a space, say S. Then if you already project it, then you project it again, it does not change the result. So that's what Christian means by linear operator that squares to itself. This is called the idempotent property. Idempotence or property. Okay, it has nothing to do with what we're doing here. Okay, a measure is simply, you can think of it as a black box, because at this stage it is indeed a black box. You don't know how to calculate a measure. Right? So it's a black box. It takes a nice set and returns a number or infinity to it. Even though we don't know how to calculate a measure based on this definition, we know its property. That's it. Okay. So hopefully we're okay with this definition. Of course, we're going to see a bunch of examples and verify the definition for these examples. All right. So here's a piece of commentary by Axler. It says the countable additivity. The countable additivity that forms the key part of the definition above allows us to prove good limit theorems. Okay, so this is something promised that will be realized in chapter 3. Note that countable additivity implies finite additivity. Yes, we already mentioned it, and we've seen this a bunch of times already. And here's how you prove it. If mu is a measure on the measurable space, yes, Mr. Repo, you're what if the set is being mean? We just ignore it, like trolls on the internet. You don't talk to them. Okay, we don't talk about measures of wild sets. Okay, so anyway, Mr. Repo, you're totally right. You're totally right, Mr. Repro. S is a bunch of sets as input for the function. That's completely correct. That's actually what sigma algebra is for. Is to specify the domain of a measure. All right. So if mu is a measure on XS, the measurable space. Oh, actually, let me turn off my. That's my WeChat. Okay. Anyway, doesn't matter. We're not going to be distracted by it. So here, if mu is a measure on the measurable space, and you have a finite collection of disjoint sets in the sigma algebra S, then the mu of the measure of their union is the sum of their measure. Right. Showing this is very easy. You simply apply the countable additivity to the sequence E1 all the way to En, and after that it's just all empty sets. This is the sequence. Right? Apply the countable additivity to the sequence, and you immediately get the finite additivity. Okay. So this shouldn't be confusing. All right. In the mathematical literature, sometimes a measure on XS is just called a measure on big X if the sigma algebra S is clear from the context. And this is especially so when X is R or a subset of R, okay, or an interval, say an interval of R. Then often S is just the Barreal sigma algebra, so it's not mentioned which sigma algebra you're talking about. Remember the definition of sigma algebra, of Barreal sigma algebra. Sometimes S is the Barreal sigma algebra. The Barreal sigma algebra is the smallest sigma algebra that contains all the open sets in R. That's the definition of Barreal sigma algebra. So it allows us to approximate subsets of R using open sets. So that's the idea of a Barreal sigma algebra. Barreal sigma algebra consists of quote-unquote nice sets in R. It avoids the nasty unmeasurable sets that we've seen in section 2C, section 2A actually, and those kind of sets will simply not be referred to again in the rest of our discussion. These are too wild for a consistent notion of measure to be defined. Okay, so that's what we're going to handle from now on. But even though, even that being said, right, having said that, the collection of Barreal the collection of Barreal subsets, aka the Barreal sigma algebra, is also very big. It contains all kinds of wild sets that are hard to visualize, but it's much smaller than the power set, and for all practical purposes, it's good enough for us to do analysis. All right, the concept of a measure as defined here is sometimes called a positive measure, although the phrase non-negative measure would be more accurate. Right. So, but sometimes you do wish to allow for negative measure. An example for that would be the notion of electric charge in physics. Right. So let's say you have a charge distribution in space. Some of them is positive charge, some of them is negative charge, and you wish to calculate the total charge. That wouldn't be a positive measure. And in fact, you can have things like complex measure as well, which will be at the very late stage of the book. Okay, so but we're not going to handle these cases at this point. A special example of great interest is a probability measure. Now, I know a lot of people are interested in measure theory simply because they wish to read rigorous probability theory literature. And in that case, a probability measure would be a function from the sigma algebra to the closed interval 0 to 1. And that's a probability measure. So mu can only be in 0 to 1. Right? Of course, a probability is between 0 to 1. That's the reason. So a probability measure is a special case of a general measure. Okay, and now let's take a look at some examples, and we're going to verify the examples in the sense that we're going to check these examples actually satisfy the definition of measure. So here, 2.55 example measures. If X is a set, then the counting measure is the measure mu defined on the sigma algebra. And the mu of the entire set should be 1. Yes, totally correct. Yeah, that's awesome, right? That's a great, that's actually one of the axioms of probability. Mu of the entire set, that's the what we call the sample space. Right? So, we're going to talk about probability theory later on, but here, this is a general measure, general positive measure. Actually, one thing is for sure, okay, just wanted to get that out of the way. Outer measure is not a measure. Outer measure is not a measure because, well, outer measure is not additive. It's not even finite additive. Okay, and outer measure is not just defined on a sigma algebra. We define outer measure for all subsets of real. The outer measure A of a set A in R is defined as follows. This is a well-defined notion for all subsets in R. So outer measure is not a measure. Now, outer measure is not, despite its name, okay, is not a measure because outer measure is not additive. Okay. However, we have not wasted our time studying section 2.1. Section 2a. And the reason for that is that when we go to the big measure, I'm just going to give a sneak peek of what is going to happen. Okay, in the section 2D, which we aim to get to today, in section 2D, the big measure, what happens is if we restrict outer measure on the Brillouin sigma algebra, then it becomes a measure. Okay, so outer measure itself, because it, here, let me just go to the theorem here. Outer measure is a measure on Brillouin sets. That is to say, if you restrict the definition of outer measure to only sets that are in the Brillouin sigma algebra, or for Brillouin sets, then suddenly the restriction of outer measure on scripted B is a measure. And that's exactly the Lebesgue measure. Okay? This is what's happening. So here you have the, because after you prove that, you can now define the Lebesgue measure. The Lebesgue measure is a measure on the measure space RB. R is a real line, B is the sigma algebra of real subsets of real, that assigns to each Brillouin set its outer measure. In other words, the Lebesgue measure of a set is the same as its outer measure, except that the term Lebesgue measure should not be applied to arbitrary sets, but only to Brillouin sets, and also to what we call Lebesgue measurable sets, as we soon will see. Unlike outer measure, Lebesgue measure is actually a measure, so outer measure isn't. Okay, outer measure isn't. So just want to get that confusion, a potential confusion, out of the way, because we already defined measure in section 2a. No, we haven't. Outer measure is not a measure, and it is in 2c where we formally define what a measure is, just as stated. So Lebesgue measure is simply the restriction of outer measure on Brillouin sets, or the Brillouin sigma algebra. Okay, so this is an ingenious construction, and it's highly unnatural if you've never seen this before. Okay, so let me just go back to the definition of measure. So there's a question in chat. What if we go to complex number? It is possible for outer measure to be a measure. Actually, I don't know. I have no clue. So if you're interested, if we go to the content, and here near the end, there is a section on complex measures. I think what he mean, Mr. Repro, he could be talking about complex measure. Actually, I forgot which section it is. Yeah, real and complex measures. Yeah, so it is possible to have complex measures. Yeah, a complex measure is a countable additive function, S to C. So that is to say, this function nu takes complex value and it satisfies countable additivity. Right here, you see in this definition, yeah, I think this is understandable, right? Yeah, just based on what we understand, what we read, we can already understand this definition. So a measurable space is a pair XS, S is a sigma algebra. Recall that a measure on XS is a countable additive function from S to this set, 0 to infinity, closed interval, that takes empty set to 0. Countable additive function that takes values from R or C gives us new objects, such as the real measures and complex measures. So this is countable additivity, nothing surprising so far. But a real measure takes a value in R. That is to say, it can't be infinite, and it can be negative. It just can be negative. And complex measures, it's the same definition, except now the R is taken as C. And earlier here, F, I believe this is a field. I believe this is a field. Big F. Axler tends to write that in, perhaps it was maybe defined earlier, but big F has to be a field. Yeah, this is a little bit different because 0 to infinity is not a field. Is it actually 0 to infinity? Is it a field? No, it's not a field because there's no such thing as a, what do we call it, the additive inverse. Additive inverse on 0 to infinity is undefined, therefore this is not a field. Here we're considering the codomain of the set function to be a field. It can be R or C. I don't know if you extend that to, let's say if you take C, then you can define it for all or subset. Probably not, and because there's the power set of R is just too wild. It's not a field. Okay. Chat says, series said, "Hi, I hope to learn from the videos demonstrating measures. I took it one semester and I had to drop out near the end of semester because getting to a D." Man, you were right. It is. Yeah, I mean, it is. I would say it's to weed out. Like, it's not say to weed. Like, this is a tough subject on its own. Like, even without the academic pressure. I understand academic pressure because, well, I came from there. Now, I mean, I have the luxury to slow things down and make discussions every step of the way, right? Whereas, say, if you take a course on measure theory in grad school, you don't always have the luxury to do that, considering other, or just advanced in the way, considering you often have other activities anyway, I don't want to get into that, right? So here, I mean, we have no other objective other than, just understand what is going on. It's simple as that. Okay, we're not here for the grade. We're not here to impress others. Okay, I'm just here to try to understand what the heck is going on. Okay, anyway, let's go back. So basically, accountable additivity can be does not rely on the values, the set of values that the function takes. If that makes sense. So yeah, so we're gonna stick to the usual measure, the positive measure, okay? And that's all we're gonna say about that. Going back to examples. If X is a set, then this is what we call a counting measure. So what is a counting measure? Well, as the name suggests, it should count the number of things in a set, right? So how do you do that? It's a measure mu defined on the sigma algebra of all subsets of X by setting mu E equals n if E is a finite set containing exactly n elements, and mu E equals infinity if it is not a finite set. So that's neat, right? So it does exactly what the name suggests. It counts how many points are there in the set. Now, how many points there are in the set E. If E is finite, then mu E returns its number of elements. If E is infinite, it returns, well, infinity. Okay, so that's the counting measure. Let's verify this. Let's verify that is actually a measure. So the sigma algebra here is the biggest sigma algebra, the power set. And when E is empty, mu of E is obviously 0 because it contains 0 element. Right? So this condition is satisfied. And because the number of elements can never be minus, right? So the codomain also checks out. So now we need to consider whether countable additivity holds. If one of the, so we consider a general, consider an arbitrary disjoint sequence E1, E2 of sets in S. And we're going to consider two cases. if one of the sets is an infinite set, then the union is infinite. So on the left hand side, mu of an infinite set is infinity, is the positive infinity. On the right hand side, because, well, one of the EKs is infinite, so the sum has an infinite term in it and automatically becomes infinite. So the case is trivial. So it's a case for, so that case is trivial, namely if you have a infinite set in the sequence. So now we can consider the situation where the subsets E1, E2, or so on are all finite. So, and this just becomes a property of the finite set. The property of the finite set. So, okay, how do we show that case? If you have E1, E2 all the way disjoint, okay, the union don't have to be disjoint, all right? The union, there's no such restriction for that. Because if, let's say, if the union is finite, if the union of infinitely many sets, E1 all the way to En, are finite, if the union is finite, that means there's only finitely many non-empty sets in the sequence, and everything else is empty. We're not going to assume that. We're going to take E1, E2 as all finite, but their union might not be finite. Okay. Actually, was that a good strategy to prove it? Because I was like, oh, if the union was infinite, then there's must be only finitely many non-empty sets in the sequence. So both sides are now empty. Sorry, not empty. Both sides are now finite. And then it just reduces to a property for finite union, where you have finite numbers on both sides. And if, let's say, the union is infinite, let's say if the union is infinite here, if the union is infinite, that must mean okay, I'll have to think it through. So Mr. Repro said, so not all sets can be finite and not all can be full or empty. Yeah, this is where I was going, right? Let's try to write this formally. So example, let me just the counting measure. So verify the counting measure is actually a measure, right? So example 2.55, the A counting measure. So we wish to verify countable additivity here. It's intuitive, but still it requires a proof. So X is a set, it's an arbitrary set. Okay, let S to be the power set of X, the collection of all subsets of X. Mu from S to 0 to infinity with mu E equals the cardinality of E if E is finite, and is infinite if E is infinite. So that's basically the counting measure. And now we need to verify this is actually a measure. Mu empty is 0, that's obvious. Maybe cardinality. Wow, there's a lot of inputs in chat. That's great. I'll take a look shortly. So here we let E1 E2, and so on, be a sequence of disjoint sets in big X, in not big S, but scripted S. Okay, so need to show the mu of the infinite union n greater or equal to 1 En is the sum n from 1 to infinity mu of En. All right, so case if one of E1, E2, and so on is infinite, then this is trivial. Okay, and in the case, say, all of E1, E2 are finite. Okay, so just need to consider this case now. So what do Chad say? So by definition, Chad says, by definition of sigma algebra, if every sequence is disjoint, brain hurts. I know, right? This is such a simple example, but to prove it rigorously, it seems not completely obvious. If the union don't have to be disjoint with the measure, in a definition of countability, in a definition of countable additivity, the set has to be disjoint. Okay, if you don't have disjointness, then you would have inequality. Say like this, just two sets will suffice. With two sets suffice to show the idea. The mu of A union B is less than or equal to mu A plus mu B. So there's going to be overlaps, right? So this way you get what we call a sub-countability. Sub-additivity, and it also works for infinite union as well. Not additivity. If you don't have, in a statement of countable additivity, the sets taking union has to be disjoint. However, if we talk about sub-additivity, then there's no need. AB can be arbitrary. The sequence can be arbitrary as well. So that's the question. But here, now we're still looking at the original problem. So you have E1 all the way to En, and so on, to be a sequence of disjoint sets. And now we assume all of them are finite. All of them are finite. So, well, in that case, the right-hand side is just the sum of the cardinalities. Right, so the right-hand side, in the summation, is just the sum of En cardinality, and from 1 to infinity. And from 1 to infinity. Okay, so this is infinite sum, so there are two cases. It can converge or diverge. Right. So remember what this means. Hang on, I'm just going to use the bathroom real quick. Sorry guys, I'll be back in 1 minute. So as I was saying, the right-hand side is the infinite series, and the infinite series is a limit. Is a limit of big N tends to infinity, the sum of the cardinality of n goes from 1 to big N. Right, that's the definition of infinite series. So there are two possibilities, whether this is infinite or finite. So there are two cases, subcase. Right, the limit star is exists, okay, or don't exist. In which case it don't exist, it's just infinite. Subcase, okay. The limit star is infinite. So which one should we do first? Remember, here, En has to be an integer. En cardinality has to be integer, because all the sets are finite. And therefore the sum is an integer. So this is an integer valued sequence. The limit here we're discussing is an integer or natural number or whatever, non-negative integer valued sequence. And in that case, if it has a limit, it has to be eventually constant. That's a fact from real analysis. I repeat that again. If a non-negative integer valued sequence has a limit, then it must be eventually constant. So, yeah, I hope that's clear. So I'm just going to write it down. Then let's call this thing an. Okay, an, a big N, defined as the sum of En cardinality n from 1 to big N is eventually constant. Since an is non-negative integer valued. All right, so that's where we're going. What does this mean then? Well, i.e. there exists, say, a big M such that there exists a big N, so let's call it big N star. Big N star, an integer, a natural number. So exists big N star equals 1, 2, and so on, such that a big N star equals a big N star plus 1 equals a big N star plus 2, and so on. It's eventually constant. But that just means, okay, but that just means the cardinality of E big N star plus 1, okay, equals cardinality of big E big N star plus 2, and so on, are 0. In which case, these sets are all empty. So En are all empty sets for all n greater than big N star. So in that case, the right-hand side is a finite sum. The right-hand side is here. The infinite sum reduces to a finite sum, n from 1 to n big N star, En cardinality. That's the right-hand side. And on the left-hand side, because the sets are all disjoint, the union, of course, have this many elements as well. The left-hand side, which is the mu of the union of n from 1 to infinity, it's now mu the union n from 1 to big N star. En. And now this is a finite set, so that's just the union from 1 to n star En taking cardinality. And this is a finite sum. This is a finite set. And that's the sum of En. N from 1 to n star. Okay? 1 to n star, and this equals the right hand side. So that's the first subcase done. Okay. Okay, so that's the first subcase done. And now we have the second subcase. The limit star is infinite. The limit star is infinite, so this is a properly divergent sequence. It's monotone increasing and it's properly divergent. So what does that mean? So it just means that if the limit star is infinite, it means none of these sets are empty. None of them are empty, but how should I put this? There could be infinite. There could be empty sets in there. There could be empty sets in there, but this means that the sequence an, right, the partial sum of the series, is unbounded. That's obvious. If the limit is infinity, it cannot be bounded. An is unbounded. That is to say, the union, is unbounded. That is to say, there must be infinitely many non-empty sets. There exist infinitely many non-empty sets in the sequence. In the sequence E1, E2, and so on. There exists infinitely many non-empty sets in the sequence, and in that case, and because they would contain at least one, right? They would contain at least one element. Each non-empty set will, of course, contain at least one element, and as a result, the union n greater or equal to 1 En has to be an infinite set. This is infinite, and as a result, mu of the union of En n greater or equal to 1 is infinite. So equals the right hand side, and we're done. And that completes the proof. Alright, so that's the counting measure. So it's that for all n there exists m. Yeah, you're right. Yeah. So basically, there exists infinitely many. You can extract a subsequence of En of non-empty sets, right? The casual polemic. Yeah, that's exactly what this sentence is saying, but equivalent. For any n, there exists m greater than n such that em is not empty. And you can do this, and because of that statement, you can construct a subsequence of non-empty sets, which makes the union of En infinite. So the mu of the union is infinite, which equals the right hand side in that case. Okay, so that's the counting measure. I would really love to follow, but definitely need to go through MIT's real analysis before revisiting this to get a proper clue. Either way, no worries. Yeah, like I do encourage you to locate the exact point of confusion to see whether this is a prerequisite issue. Okay, I know like measure theory is a prerequisite heavy subject. Okay, but the most important prerequisite is just proofreading and writing, the ability to manipulate sets rather than specific results in set theory. Okay, so when you get stuck, which you will, this is everybody's experience in measure theory, try to locate exactly where you got confused. Is it because of a new notation? Is it because of a definition in the theory that we have not yet internalized? Or is it actually a real analysis prerequisite issue? So try to locate the exact point of confusion. Okay. So sometimes, if you think, let's say, if you think you got confused, and try to locate exactly the missing piece in the prerequisite text, might not be the best strategy. Just look at the new concept itself. Of course, there's certain points where you say, "Oh, I'm completely lost. This is totally beyond me." Then go ahead, like talk to a more experienced person and see exactly what went wrong. Okay. Anyway, so let's come back. This is the simplest example, okay, counting measure. And now let's take a look at the second example. This is called a direct measure. Suppose X is a set, and S is sigma algebra, and C is in big X. All right, C is a point. To find the direct measure, direct delta, right? This is a direct delta. Actually, not quite. But the name suggests a connection. Not the direct delta, but it's called a direct measure. The direct measure, let me finish reading this example before I come back to chat. To find the direct measure delta C on the measurable space XS by the following. Delta C of E. Of course, what is E? E is a member of the sigma algebra. This is implied at this point. Okay, the sigma algebra is a domain of delta C. So E is a point, or not, actually E is a set. E is a set in S. The size of E according to the direct delta symbol, direct delta measure, not direct delta measure, it's called direct measure. I said direct delta a few times, okay, that's not the name. It's called direct measure. The direct measure of E is 1 if C is in E, and 0 if C is not in E. So this is interesting. It kind of works like a, like what? Kind of like a indicator function, huh? Kind of work like indicator function. Recall that an indicator function of a set, say A. Okay, let A be a set. Let's just for the sake of argument, let's call it S is in the sigma algebra. All right. The indicator function, usually denoted as 1A in probability theory, is written as follows. So if omega is an element in big X, then 1A of omega is 1 if omega is in big A, and 0 if omega is not in big A. What's the difference here between the direct measure and indicator function? What's the difference here? Well, the difference is in the argument. Even though on the right it looks completely the same, the perspective is different. So for the indicator function, the set A is fixed. Okay, so this is your big X, this is A. You already selected A. And now you define the function, indicator function 1A, as a function on big X. That is to say, for any point omega in big X, if omega is outside of A, the function equals 1. If omega is inside, if omega is outside A, it's at 0. If omega is inside A, it's 1. This is a function of omega. It is a function defined on big X. The direct measure, on the other hand, even though the right-hand side looks similar, it is defined over the sigma algebra. So that is to say, in direct measure, C is fixed, the point is fixed, the set is a variable, whereas in the indicator function, the set A is fixed and the point is variable. That's the difference. The difference in perspective, kind of like how we like in probability theory. In mathematical statistics, the likelihood function equals the probability density numerically, even though the perspective completely changes. And this is exactly what's happening here. The direct measure is a function of set, whereas the indicator function is a function of point. Subtle difference. Okay, so yeah, this is named after Paul Dirac, worked in relativity, quantum mechanics, blah, blah, blah. Hopefully we'll see some physics down the road in the channel, on the channel. Let's read the chat. Chat says, is this about breaking things into disjoint sets and understanding that you can construct union statement by utilizing complement? Yes, very much, very much. So we have the definition of measure here, right? Where we set up this property called countable union, and that's exactly how we're going to approximate more complicated sets using countable union. All right. Agreed. Prerequisites don't need to be a hard and fast rule. I spent months not diving into a new research project because I saw that needed measures area as prerequisite. Yes, exactly. You see, sometimes prerequisite hoarding can be a form of procrastination, while at the same time giving you an illusion that you're actually making progress. So this is actually a form of procrastination, I'll be frank. And often, this is not entirely students' fault, because I would say the biggest culprit is more cultural. Because you see, in a university, there's this system of prerequisites, official prerequisites that are strictly enforced. In a university, there's this strict prerequisite system that is enforced. So a non-expert can easily believe, oh, you actually do need to pass this course to get on to the next, otherwise you can't understand a damn thing. That's typically not how it works either. Okay, so really is if you really want to say, for example, I'm in a similar situation actually, guys. A personal story, not story, but situation. And actually, if you guys are knowledgeable in this, please let me know. For example, I want to get into Lie theory. Yeah, seriously, I want to get into proper Lie theory, but I don't have a strong background in algebra. So now I'm wondering, okay, what kind of group theory do I need? Like, what should I do? Like, do I just go to Dummett and Foote and do the group theory there? Is that good enough background for getting into Lie group, Lie algebra, and representation? I don't know, right? Because that's the thing. I don't have a formal background in algebra, and now I wanted to learn something that whose official prerequisites always say, oh, you need group theory. Like, what should I do? Perhaps I should do that live to illustrate what I was talking about. Maybe I will get stuck because of the lack of formal prerequisite. Maybe I get stuck simply because I don't understand what is actually the new thing in the Lie theory itself. Okay, not a prerequisite issue. Perhaps it was a notational issue. Perhaps I didn't understand the example. That kind of thing. Let me know in the chat if you guys want to see that kind of process. And of course, let me know if you're interested also in Lie theory. And let me know if you're, also let me know if you're in a similar boat, that you never took, let's say, a formal course on group theory, but you now wanted to get into, say, things like Lie theory for other applications. Okay, I think this will be a wonderful discussion here. Yeah, I'm trying to learn stochastic process up to Langevin Fokker-Plante. Are you doing videos or have? Good, very good actually. I was just thinking about it because I haven't posted a video about stochastic process or stochastic calculus in about a month, and I think it's time to get back to it. I think it's a very well time to get back to it, and we will do a stochastic live next week, because this week I still have some more things to finish, so I can't get back to stochastic this week, but definitely stochastic coming up next week. And guys, you know what? Because of this comment, we will do Fokker-Planck next week and also Black-Scholes next week. How about that? So yeah, I'm just gonna write it in chat. Okay, so Fokker-Planck. I don't know about Langevin, but definitely Fokker-Planck next week, because actually it goes well with what we're doing already today. Not today, but yesterday. Stochastic processes and PDE. Fokker-Planck next week. Black-Scholes, also Black-Scholes. So this way, both physicists and financial people, quant people, are happy. Also next week. It's going to be a great week for the stochastic folks next week. All right. So here, coming back to the direct measure. Oh, hi, Leo. Thank you very much for joining the stream. So here we have the direct measure, and we now need to verify this is actually a measure. And just a quick word, why it's called a direct measure. Because in physics we have, or not just in physics, but in the theory of distribution, there's this weird, crazy function called direct delta function. It has this property that it equals 0. It equals 0 everywhere except 0. So delta of x is 0 if x is non-zero, and is quote-unquote infinity when x equals 0. So it's everywhere 0 except at 0, and at 0 it shoots up to infinity. So this is supposed to model things like point mass, point charge, where all the mass or all the charges are concentrated at one point with no volume. So of course this is undefined, right? When x equals 0, delta equals infinity is simply an undefined function. But instead, the defining characteristic of direct delta is that it has this normalization condition. So the integral from minus infinity to infinity delta x dx is 1. There are many ways to interpret this. You can think of it as a Gaussian distribution with 0 variance. A Gaussian distribution, of course, is a bell curve. It satisfies the normalization condition. And when the spread tends to 0, it degenerates to this direct delta. We use this all the time in physics, in also applied mathematics. We're solving PDEs and whatnot. So you can think of it as you can interpret this this notion intuitively as follows. So here you have the point mass at x equals 0, and the total mass is 1. Okay, so the position is now fixed. The position of the point mass is now fixed, and let's select a subset of R and just calculate how much mass in there. Okay, because in our setup the point mass is at the origin, and there's no mass elsewhere whatsoever. So if you select a subset E that does not include the point mass's location, then you get 0 mass. And if you select the E to contain x equals 0, then it suddenly shoots up to 1. So you can think of this function as a kind of a minesweeper. It's a minesweeper, like, you know, in those war movies where a soldier like this carries a rod with a piece of ring attached to it. Right? So this is your set E. It can be swung around, right, to detect if there's a landmine under it. Right. Okay. So yeah, that's the direct measure. Why is direct delta tricky for measures here? Well, the direct measure is not tricky at all. It's very simple. It's how to make sense of this function. How to make sense of this supposed function? That's what is difficult. And how do you say differentiate this crazy fella? How do you differentiate? Yeah, because in physics sometimes you wanted to differentiate this. So the notion Dirac delta is physically intuitive but mathematically ambiguous, and it wasn't formalized until this person called Laurent Schwartz, I believe. Laurent Schwartz, a Fields medalist, and also Sergei Sobolev, who independently invented the distribution theory, and now you can differentiate this crazy thing. Yeah, if you select an E contain me, you will find quite a lot of math. Holy yeah. I saw something optimal transpose theory. There's a problem broken down one if. Sha, actually, I have no clue. I have no clue. I have. The tricky thing is about its density. The measure itself is not tricky, and I have very little comment to say about optimal transport. Yes, often you need to do integration by part with the Dirac delta. Exactly. That's how you differentiate, quote unquote, differentiate. Right? You pass the differentiation to a test function using integration by part. But we're getting way ahead of ourselves, and it's unrelated to this point. But it's a fun object, right? To define derivatives of this crazy object, you need integration by part, and that's exactly the trick. It's an ingenious trick. Anyway, enough about distribution theory. Well, stick to applied math with no proofs. Taking some notes on the Koopman operator theory right now. Okay, that's cool. Yeah. Well, Sha just mentioned optimal transport theory. Optimal transport is also very dense. The barrier of entry is very high. The minimum for that would be measure theory and functional analysis. Anyway, here, we've seen this example. Time to do the proof. Direct measure. So once again, we start from a general set, big X. X is a set. Scripted S is a sigma algebra. And C is in X, a point. So delta C is from S to 0 to infinity with the following definition. Delta C of E equals 1 if C is in E. You caught the mine. And if C is not in E, is 0. Which to prove that it is indeed a measure. Well, so first of all, delta C empty set is 0, which is trivial. Empty set cannot contain an element, so it cannot contain C. Trivial. All right, so that's the first thing. And now we need to prove the main thing, right? Namely countable additivity. So let E1, E2 be an arbitrary sequence in the scripted S. Yeah, sure. Leo, thank you very much for stopping by. Awesome new video, by the way. Yeah, guys, Leo posted a new video, an update on AI in math. I don't know, like I have mixed feeling about this. It kind of scares me, but anyway, this is, I guess, normal in a time of change. We'll see how things go. Let E1, E2 all the way be a sequence in S. Need to show. Okay, the mu of discrete disjoint actually needs to be disjoint, not an arbitrary sequence. Need to show mu of the union as the sum of mu of En. This shouldn't be too difficult, but let's just verify that. So what are the possibilities here? Looking at the left-hand side, what are the possibilities here? So either the union contains C or don't. Well, actually, I should use delta C. So you can think of the point mass location is in is at C. That's the coordinate of the point mass. So there you go. You have the big set X. Yeah, it can only be in one set. That's exactly what happens. Yeah, you nailed it. The casual polemic. Thank you very much for your input. So basically, that's exactly the trick, the observation. So we need to show this identity, delta C of the union equals the sum of delta C. Right, so let's consider two cases. First, none of them, or I should say, just take the union. Okay, if the union of infinity, union of 1 to infinity En contains C, and the second case is they don't. Okay, so for the first case, that means there exists N equals 1 to all the way, such that En, called N star, okay, little n star, contains C. And because of disjointness, since E1, E2 are and so on are disjoint, this means En not includes C for all n not equals n star. Not equals n star. So the right-hand side, therefore, first of all, the left-hand side is 1. Right? The left-hand side is 1, and it's the mu of En star. Not the mu of En star, but rather the delta. Yeah, basically only one. See, only En star can have C, and no other sets can have it. So all the terms in the summation only have only one term being 1. Everything else is 0. So basically we're done. Right? That's delta C of En star, and it equals the sum of delta C of En from 1 to infinity, which is the right-hand side. Okay, so that's the first case. And the second case, if it's not in the union, which means, well, it's not in any. So En does not include C for all n, both 1, 2, and so on. So trivially, left-hand side and right-hand side are both 0. So we're done. So this is actually a lot easier than the previous example. Right? So there's that. That's the direct measure. We verify the axioms. The third bullet point is if X is a set and S is a sigma algebra on X, and W is a function from X to from X to 0 to infinity. Okay, interesting. So define a measure mu on the measurable space XS by the following. So mu of E is the sum of W of X, where X ranges over E. Here E is an element in the sigma algebra. So, of course, this needs to be explained. When E is finite, the summation is well understood. It's just a finite sum. If E is infinite, then you don't necessarily even have a series, because E can be uncountably infinite. In that case, the sum is defined as the supremum of all finite subsums. So this is defined as the soup. Okay, this way we can actually define uncountable sums. Okay, sum with uncountably many terms. So this is the soup of the sum of Wx, where x ranges over the set D, where D is a subset of E and D is finite. So that's the definition of this sum. It ranges all finite subsets of E. Okay, interesting. So can we give this a physical interpretation? Is that possible? Well, before we dive into the proof, let's just want to see what's the main intuition here. So W of x. So can we think of, say, x is a country, right? X is a country, and it contains of cities, or just a human habitat. Okay, cities, towns, whatever. You can think of them as a bunch of points. Right, and W, you can think of W as wealth. How convenient, right? You can think of W as wealth. So W of x is the wealth of a city. X is a city. Little x is a city. S is a sigma algebra. E is a nice set. Is a nice subset in E. A nice subset in big X. So you can think of E as a region in a country, like a province or a state. A mu of E would just be the total wealth. Okay? It's just the total wealth of that region. And this can be thought of as a measure. That's the that's the example was about. All right, so let's try to prove it. Okay, lots of examples. So very nice exercises. C. So does it have a name? It doesn't have a name. Okay, so yeah. So just let X be a set. Scripted S is a sigma algebra. W is a function from X to the interval 0 to infinity. Okay, and mu of X, mu is from S to 0 to infinity, closed interval, defined as follows. Mu of E is there's no case, it's just the sum of X in E, W of X. Okay, this is defined as the supremum of all finite sums, finite subsums, where D is a subset of E, D finite. Okay, so that's mu E, and let's do a proof. Okay, how do we prove this is indeed a measure? So first of all, well, if E is empty, then there's nothing in there. Right? The sum has no term, it's just 0. This is trivial. Okay, so always we want to show countable additivity. In fact, you know what? Let me just copy the statement here, do a little bit of a change. Now, you let E1 to E1, E2, and so on be a disjoint sequence in S. Need to show mu of the union is the sum of all the measures. So we want to do that. Let's do the proof. How do we go about showing it? Hmm. On the left is a supremum. So this is a sup. Okay, let me just write it down. By definition, the left-hand side is the supremum of of the sum x over d w of x, such that D is a subset of the infinite union, of the countable union, and D is finite. Okay? There's that. And on the right we have an infinite series. On the right we have an infinite series. So how can we say on the En, these are, so at least can we prove one direction, no? Can prove one direction. Let's say if we consider a finite sum, a finite partial sum for the right hand side, because the left hand side is supposed to be the supremum. This is supposed to be the supremum, so it's like the maximum. So at least can we show this is greater or equal to all the partial sums on the right. Can we do that? So let's start out, make a decreasing set. Hi Steve, thank you very much for joining the stream. Yeah, you see this feels kind of obvious, right? It feels kind of obvious. I was saying like this can be interpreted as a wealth in a region, where you're given the function w that measures the wealth of each city. But proving it, because of potential infinity going on, it's not completely obvious. Maybe make a decreasing set. I mean, we haven't even introduced, like, say, for example, monotonicity yet. So hang on. Okay. Hi, Steve. Yeah. So as I was saying, can we consider, say, usually when you prove an equality in measure theory, you do it using two inequalities. In real analysis in general, it just feels more likely to succeed. Okay, so as I was saying, maybe we can try show left hand side is greater or equal to the right hand side, but for that, all right, we need to show left hand side is greater or equal to all partial sums. Left hand side greater or equal to right hand side. Right? That's of course that's the two main direction, right? Left hand side less than or equal to the right hand side. But how do we realize such goals? Here, okay, for this part of the proof, it suffices to show that the left hand side is greater or equal to the partial sums n from 1 to big N mu of En for all n equals for all big N, right? And then you take the limit, you get the left hand side greater or equal to the right hand side, right? So that's an idea. Still not sure this is gonna play out nicely though, but let's try. Greater or equal to the right hand side. So this is our idea. Does that work? Mu of En. remember, mu of En is at a, say, mu of En is a bunch of, and mu of En is also a bunch of soups. That's a bunch of soup as well. So what we're trying to say here, the left-hand side, in the left-hand side, so here the D is, oh, thank you very much for joining the channel member. Yeah, it's a soup. I know, like, this is, can we say, actually, can we say things like this? The left-hand side, by the definition of, by star, can we say the left-hand side is greater or equal to the soup of the sum x over d, w of x, such that d is, because now we have, we fix n, right? Suppose we fix big N. Suppose we fix big N to be arbitrary. Fix big N in 1, 2, and so on. Can we say by star the left-hand side is greater or equal to the soup of the finite sum of wx, x in big D, and D belongs to, D is a subset of the finite union. Can we say that? D is a finite set and is a subset of the finite union. Let's think about that. I think this is okay. I think this is okay because now you have this set right here is a subset of this. Is a subset of this. And when you're taking a soup over a bigger set, it should be always greater or equal to the soup of a smaller set. Yeah, thank you very much. Thank you very that's much appreciated. Yeah. So here we have this little property here. But this is just because if you replace big infinity by big N, right? You get a subset of this set. The finite sum form here is a subset of the finite sum form here. There's that. And so D is finite. Let's think about that. So D is finite and is a subset of a finite union. So you can decompose here for any D that is a subset of this thing. You can partition or decompose D into parts that comes from E1, parts that comes from E2, part that comes from E3, all the way to part that comes from En. Can we do that? I think we can. I think we can. So suppose, let me just write it this way. So suppose you have, suppose D is finite. A set D is finite. And D is a subset of the finite sum. Since En and greater or equal to 1 are disjoint, we can write there exists D1 there exists D1, D2 all the way to D actually, you don't need finite assumption. You don't need actually just d1, d2 all the way. d1, d2 set. Now, for any such d, you can always decompose d into d1, d2, and so on, such that they are disjoint. And the union of n greater or equal to 1, dn is d. And you have dn is a subset of en for all n. So all of these properties. Does that make sense? Because the union of, say, E1, E2, E3, I'm just going to draw three sets, say E1, E2, all the way to En is like this. Okay, these are disjoint. And D is a subset of all of them. So there's got to be a part, say, D1. It can be empty. And then a part D2. D1 is a subset of E1, D2 is a subset of E2, and Dn is a subset of En, and it keeps going. Their union is D. D is a subset of the disjoint union. So D can be written as a disjoint union. That's my point. And each part, Dn, comes from En. Okay, so here I'm just trying to argue that, okay, these are finite. Yeah, D is finite, so these are all finite, obviously. So Dn are all finite. It's clear from this setup. So the sum of, say, how do I put this? I need the mu. So mu En, right? Mu En is greater or equal to the finite sum x in Dn Wx. Yeah, sum of Wx. So Dn is finite. Mu En is the soup of the finite sum, right? Of the finite subsums. That's the we have this relation. So here, can we say go from the left to right? Conclude left is greater or equal to right? Well, taking summation on both sides, sum of mu En and greater or equal to 1, that's the right hand side, right? The right hand side is supposed to be, hang on, this is supposed to be greater or equal to, greater or equal to the double sum. That's not what we wanted, though. We want the right hand side, this is the right hand side, to be less than or equal to something. We want the right hand side to be less than or equal to something. Not quite what we wanted. All right, so so we create a okay, why did you retract? I was trying to read it. Could be useful, man. Anyway, hang on, let me just take a look at Axler. And just to make sure we understood everything correctly, okay? Just want to make sure we understood everything correctly. So that's the measure, let's call it the wealth measure. So how do we prove countable additivity? Okay, so yeah, here we want the left hand side is perhaps this. We can ignore the big N because I didn't use this, right? I never used this big N. So what would be an upper bound for the right-hand side? The right-hand side is a sum of a bunch of soups, right? The right-hand side is a bunch of soups. Soup has a property, no? Guys, soup has a property. I think there is a property of soup. Maybe it's in Axler's supplement. Hang on. Axler's supplement, measure series supplement. I should have that with me. Let me just go find it in my folder here. So yeah, there should be a property of soup that says the soup of the set A plus B equals the soup of A plus the soup of B. I don't know if there's an infinite generalization of that. So that's the issue here. Soup, yeah, this is a well-known exercise, should be. It should be a well-known exercise. Like the soup of this, yeah, right here. This is a classic exercise. Here, A plus B is defined as this. So the sum of two sets, right, A and B are subset of real, is defined as A plus B. A is in big A, B is in big B. So let's think about, can we generalize this to countably many sets? Say A1, A2 all the way. So on the right you have an infinite series. And on the left you have to define the sum of infinitely many sets, which is okay because you just form the, actually, is that okay though? Is it okay though? So, well, if all of them are non-negative, I suppose that's okay because you have A and B non-negative. And the series either converges or is infinite. Either way, it converges in the extended sense. So I think it should be well defined. A1 plus A2 plus all the way, right? The sum of infinitely many sets should be well defined. So maybe that will do it. Okay. Here, you think about it. So here you have the set A and B being non-empty subsets of the extended real, 0 to infinity. So I'm going to change strategy, okay? I'm going to not do this, but say I want to show that still, I mean, I still want the main structure of it. I want to show two inequalities. Can we maybe try the other direction? Because maybe we'll have better luck there, okay? So here we want to show the mu of the union is bounded by the infinite series. Okay, and in fact, let's give this a notation because I hate writing infinite unions all the time. So let's just write this as big E. Okay, so let's just write the union as big E. It's kind of interesting that Axler provided no steps whatsoever. They just stated, right? That's kind of rough. So here, I'm just going to write this as E, okay? And the left-hand side would be, yeah, let's write that as big E. Just to save some writing, nothing is substantially achieved at this point. I just want to do the other direction. That's what I'm trying to do. So I wanted to show essentially subadditivity. We just get rid of this now. Okay, so I want to show subadditivity. This is what left hand side less than or equal to the right hand side mean. So let's say I want to do this now, okay, and I don't know about what's going on up there. Okay, so how do we go about showing this? Left hand side, you have a finite. Let's pick a finite set. Let's just first of all take any finite set. D, which is a subset of E. Okay, and let's write D in the following way, because the picture I just erased actually is still kind of helpful. So this is E1, E2, and so on. Right? This is En, and it keeps going. D is a subset of that. What I'm trying to say is those little D1, D2, Dn, and so on are simply the intersection of D and En. So let's write, since En's are disjoint, we have D is the countable union, n from 1 to infinity, D intersect En. Okay, so we have that. But think about it, right? D is finite. Think about D is finite. So that means in this union, only finitely many of these intersections are non-empty. So since D is, well, finite, okay, I'm just exploring options, okay? I don't have a definite direction yet. Okay? Just trying to see what sort of conclusion can we get, because D is finite, because this is something I did not use last time, and it could be useful. Only finitely many sets among D intersect En, n equals 1, 2, and so on, are non-empty. Okay. So can we write the sum? Because to talk about mu e, you have to do the finite sum. What about the finite sum? What does that mean for the finite sum? The finite sum, sum of w of x, where x is in D, is what? Well, this is D. Here, this is a picture of D. So, well, that's the sum of n from 1 to infinity. The sum of x in the intersection D intersect En, w of x. That's the identity. What else do we have here? Here, because for each of these sets, that is D intersect En, that's a subset of E. That's my point is, this is less than or equal to mu En. This is less than or equal to mu n. Let's think about why. Okay, mu en is the sup of the sum. Let's just use a different notation. Say d prime x over d prime, and d prime is finite. Called let's call it dn. Okay, x is in dn, w of x, such that dn is subset of en and dn finite. Right here, d intersect en is finite. Yeah, that pretty much this is finite, so this is less than the sup. So therefore, this is less than or equal to the sum of n, because I want to create this less than or equal to this infinite sum. Actually, yeah, this is correct, but the previous sentence is not useful, right? I didn't use finitely many on empty. It wasn't used. But basically, this is what we have here. For any finite set, D, it's a subset of the union, we have the sum, the finite subsum over D is less than or equal to the infinite series. So now you just take the supremum on the left-hand side over all possible D, and you get what we needed. So that's kind of nice. Okay, so let me just erase the useless part. Okay. Okay. So, yeah, this is. I think this is pretty good, huh? Yeah, if I do say so myself, then this should be pretty good. So yeah, let's delete that. So basically, then this is true for all finite set D. And now you take the sup on both sides. Take the sup over all D, and we get the mu of x, mu of e is less than or equal to the infinite sum. From 1 to infinity. All right, so that's one direction. Okay, so for the other direction, we need mu of e to be greater or equal to. This is where we somewhat got stuck last time. So we still need this direction here. So how do we get this inequality? I guess you have to do some funny business with the definition of supremum. Remember, the supremum is the greatest lower bound. Sorry, the least upper bound is the least. The supremum is the least upper bound. That means if you, let's say, go a little bit under the supremum, it fails to be an upper bound. It fails to be an upper bound. So I think we're going to do an exploitation of the Zeno's paradox. Remember, we used that trick early on in the earlier episode. Remember, how do we show a countable set has measure 0, has an outer measure 0, right? You have a countable set. You're going to exploit the geometric series. To use the geometric series to squeeze the total length of the interval that covers the finite set to be as small as possible. So I think that's the trick here. So yeah, to show this, for each n equals 1, 2, and so on, we're going to pick a finite set Dn, which is a subset of En. It's the same image. I keep erasing it, right? But it's actually quite helpful for our visual. So this is E1, E2, En, and so on. We're going to pick a finite set from them. Let's say D1, D2, Dn, and whatnot. Each of them is finite. Because of mu of En is a supremum, such that you can cook up this construction. Say, I'm going to abuse the Zeno's paradox because I really want to have a greater than sign. See what I'm saying? So I really want to have the sum of x over dn w of x. This is greater or equal greater. This is greater than mu of En, greater than mu of En, minus a little thing. Minus a little thing. And because I know I'm eventually going to sum over the left-hand side, I want the little thing to be also summable. This is what we mean by exploiting the Zeno's paradox. This is our experience when handling earlier examples. You can always do this. Okay. So now, once again, because of D are all are disjoint, right? The big D is the union of all the D's, and then you can just sum over both sides. But the problem is here the D's are finite, right? The union of all of them might not be infinite. Remember, in the definition of mu e, you still need to use a finite set, a finite subset of the union. If I simply union all of them, they d1 union d2, union dn, and so on, okay, this still might not be finite. So how do we get around that? Well, I guess you simply stop at a certain big index. Let's say it stops at big Dn, right? So let's just fix a particular big N equals 1, 2, and so on, and consider this set. Consider, say, D big N. Say this is big D big N, and say that's the union of Dn, n from 1 to big N. This is a finite set. So consider this set, then Dn is a subset of the infinite union, obviously. Is a subset of the infinite union of En. And Dn is finite. D big N is finite. And now let's do the summing business. Let's do the summing business. So this way, I don't want to erase this again. Might be useful later. So this is what we're getting at. Because Dn is a finite subset of the union, of the infinite union, you can use this relation, use the definition of mu e. Therefore, mu e is greater or equal to the sum of x in Dn. Okay. This is purely for creating a finite set. If I just take the infinite union of all Dn, you might get an infinite set, which is not what the definition of the sum asks for. So that's why I'm using this big N. But it should be this should be no more complicated than if you really use an infinite sign. Okay. So here, what we're doing here. So well, we're going to sum over this thing. We're going to sum over this thing. So by the disjointness, this sum is simply the finite sum n from 1 to big N, the sum of x in dn, w of x, and this is greater, right, using the trick here, the Zeno's paradox trick, 1 to big N, 1 to big N, and then a mu of En minus the little number there, minus the epsilon. Sorry guys, I'm not looking, I haven't been looking at chat. I'm just trying to push as far as possible. All right. So what else is going on here? Well, here, so overall, this is what? This is, you can, of course, this equals the sum of mu En, n from 1 to big N, minus epsilon, the sum of 2 to the minus n from 1 to big N. And this is, you can, this is less than 1. This is less than 1 because 1 is would be the sum of 2 to the minus n. N goes from 1 to infinity. This is less than 1. So this would be greater than the sum of n from 1 to big N, mu En minus epsilon. Minus epsilon. So, and now you can take big N to infinity. Right, take big N to infinity. So, I forgot to write let epsilon greater than 0. Okay, which is arbitrary. So, first of all, take big N to infinity. We have mu of E is greater or equal to the infinite sum. Okay, and finally, since epsilon greater than 0 is arbitrary, yeah, I was thinking about the finite sum earlier. Yeah, so it just have to, you need to cook up this this minus epsilon thing. Otherwise, here, you see where I got stuck there? You see where I got stuck here? Because the inequality should be the other direction. And this is not what we needed. And now this is okay. Okay, so that's a good review, right? A good review of an old technique, abusing Zeno's paradox. This is I think this trick is so common in measure theory that Terence Tao call it abusing, quote unquote, abusing Zeno's paradox. Yeah, Tao's. I remember him saying that in one of his blogs. So this pretty much follows, finishes the proof. So mu E is greater or equal to the sum of mu En, n from 1 to infinity. All right, so there's that. Okay, let's delete this part. So now countable additivity is shown. Okay, usually one direction is easier. and this is the second direction. Sorry guys, that's my WeChat. Gosh dang it. How do I stop this spam? Let me, dang it. That's the problem. Guys, sorry about that. I'm going to grab my phone and log out of the WeChat. Actually, you know what? I can do it here, guys. Let me just do that real quick. Close off WeChat. Sorry, guys. I haven't been looking at the. What's that? The chat. Okay. I'll be back in a second. Okay. All right. That's cool. Um, thoughts? Thoughts in chat? Sorry, guys. I haven't been following chat actually. Yeah. So, Steve, what are we trying to prove? We're trying to prove this is a measure. Here, we're trying to prove this is a measure. Part C is a measure. So I was saying, think of X as a country, and W is a function that gives you the wealth of every city in the country. So the country consists of a bunch of cities, all right? And mu is the function that tells you the total wealth of a region. So E is a region, and then you just sum over the wealth of the cities in that region. I want to prove this is a measure. The tricky part, of course, comes from the potential infinite sizes in E, right? E might not be a finite set, so we adopt this definition for a potential infinite, uncountable infinite sum. So that's defined as the supremum of all finite sums. Okay, so that's what we're trying to do. And just once we finish a proof, let's just try to read from the beginning and what else we'll see what exactly we did. Okay, to first of all check everything, and second, is there any techniques other than the Zeno's paradox? Other than that, anything we can so to say recycle and generalize and transfer to other problems. Okay, here, yeah, we in the first inequality, yeah, we need to prove two inequalities exactly. This is usually the case in analysis. In analysis, proving inequalities is much more common than proving equalities. And actually, when you try to prove equality, you do it using inequalities, and this is usually very commonly how this is done. You take two directions and prove them individually. Okay, so the first direction is easier. The first direction is easier because think about the definition of mu. Think about the definition of mu. The definition of mu is the definition of mu is a supremum here, over here. Definition of mu of E is a supremum. So consider the finite set D, and we're going to decompose it into pieces so that each piece comes from one particular En, and that piece is going to be D intersect En, which is of course a finite set. So the sum of Wx over D intersect En is less than or equal to mu n, and then you sum over that, you get for any finite set D, the sum of Wx, x over D, is less than or equal to the right hand side. And this is true for every finite set D, so you just take soup over D and boom, one direction done. Now, this is typically proving inequalities. Proving equality. Well, one inequality is easier, and this is the easier part. And here, to cook up the other direction, we abuse the Zeno's paradox, as named by Terence Tao. Right? We have seen this. So D intersect only finitely many En. Yeah, even though that's true, it didn't actually wasn't actually needed. So I was tempting to say, right, D is finite, right? So only finitely many of these intersections, D intersect En, are non-empty. It's got to be that case, but it really wasn't needed. What matters is that D intersect En is finite. Yeah, D is finite, so that D intersect En is finite. So this inner sum is bounded by mu n. And that's it. Right? So D intersect only finitely many En, even though that's true, it wasn't needed. Okay, what matters is D intersect En is finite. Right. So, and in the second direction, because, well, this is a trick that we needed, epsilon times 2 to the minus n. It's been, in section 2a, this technique was useful multiple times. And now you just, here we need to do this for a finite set Dn, because if you simply union all the d little n's, you might get an infinite set, so the definition of mu may not be applicable here. The definition of mu might not be applicable, so we deliberately cook up a finite set called Dn. And of course, Dn is a finite set, it's contained in the infinite union, and you can use the inequality mu e greater than the sum of Wx, x in Dn, and the rest should be rather straightforward. Now, it's just that this trick, epsilon times 2 to the minus n, is something that we need to get used to. All right, so here, let's see if there's any more. Well, here in the next bullet point, we'll finish this actually. We'll finish this and we'll go to Ash's book. Okay, go to Ash's book. So starting this stream on measure theory, we're going to split the our sessions in half. Okay, Axler first, and then Ash. Ash's has a more probability flavor to it. Okay. Suppose X is a set and S is a sigma algebra on X, consisting of all subsets of X that are either countable or have countable complement in big X. Define a measure, mu on the measurable space, as follows. So if E is countable, then mu is 0. If E is uncountable, then it's 3. Okay, so the sigma algebra is just a power set. Oh, sorry, no, not that sigma algebra. It's not all subsets. We've seen the sigma algebra earlier. Yes, Steve, you're totally right. So I was saying that this sigma algebra is something we've seen earlier. This is indeed a sigma algebra. We checked that. It's the collection of subsets such that it is either countable itself or its complement is countable. It's if we go back to say sigma algebra, here, this is one of the examples right here. let X be a set, then the set of all subset E of X such that either E is countable or X minus E is countable is a sigma algebra. And it was verified in one of our notes. So let's go here. Perhaps it's way earlier, I believe. This looks like exercises. Sigma algebra here. Yeah, here, sigma algebra. Either E is countable or X minus E countable is indeed a sigma algebra. You verify the axioms. Empty set is in there. Closed under complement. Closed under closed under what? Closed under countable union. So that's indeed a countable. Sorry, that's indeed a sigma algebra. That's indeed a sigma algebra, and here we have the. Oh, that's the supplement. No, this one. I'm going to definition of measure here. Yeah. So we're defining a measure on that measurable space. It says if E is countable, then it's just 0. Mu is just 0. If E is uncountable, for some weird reason, it's 3. I have no idea why 3 is chosen other than, say, 1. But this is what it is. And we need to show that this is indeed a measure. Okay. And this is indeed a measure. And actually, after finish proving this one, we will go to ASH. Because the next 2 bullet points are already mentioned. The fourth bullet point says the outer measure. The outer measure is not a measure because it's not finite additive. And the last bullet point is actually the crown jewel of this chapter. This is the crown jewel of the chapter that says if the outer measure is restricted on the Borel sigma algebra, it turns out to be a measure. Something that is very difficult to prove. All right. Here we're gonna do this part of the proof. Sorry, not this part of this proof. Just prove this example. Okay, and here we're gonna finish this and go to Axler. Not Axler, but Ash. So suppose X is a set and S is a sigma algebra on X consisting of all the subset of X that are either countable or have countable complement in big X. And define a measure, mu, on the measurable space, X and S, as follows. Okay, so proof. Yes, 3 if E is uncountable. Yeah, it's kind of weird, right? I have no idea why this is 3, but I guess we'll just follow it and try just to prove. And we'll see if whether, and pay attention, I mean, when we're doing the proof and see where, if any, 3 plays a role. Okay, or is the number really just arbitrary? So let's do the proof. So first of all, the empty set, mu of empty is of course 0 since empty is countable. Okay. So in Axler, the countable sets consist of both countably infinite sets as well as finite sets, including the empty set, which is finite. Right? So there's that. You have this part of the property trivially hold. And now let's let E1, E2, and so on be a disjoint sequence. In big X. Now not in big X, but in the sigma algebra. In the sigma algebra. So what does this mean? It means either they have, either they're countable themselves, or they have countable complement. This is what it means. Either E1 for each n. Okay, this means for every n equals 1, 2, and so on. Notice that at most one of the en can be uncountable. Why? Oh, is it because of disjointness? Actually, Steve, why is that? I was about to say, for each n, either en countable or its complement x minus en is countable. Right? That follows from a definition. S is the sigma algebra consisting of all subset of x that are either countable or have countable complement. Um, and we need to show countable additivity. So we need to show this. Okay, you type, okay, and I'll do my own thinking. I'll keep an eye on chat. So, how do we define a measure? This is the measure, the union of en. Let's perhaps do the simplest case, all of them countable. And a countable union would be still countable. Yeah, countable union of countable sets is countable. So do a case here. Suppose ENs are all countable. In that case, the union of En is a well-known result. The countable union of countable sets is countable. So, which means the left-hand side is 0, and the right-hand side would be the sum of 0, the right-hand side. So that's a trivial case as well. Okay, so that's the first case, and the other case would be, well, if one of them is either countable or have a countable complement. Say if one of them is not countable, one of ENs are not countable, is not countable, at least one of. There exists an EN that is uncountable. Okay, say En star. So En star is uncountable. If En star is uncountable, that means the complement x minus En star is countable. It has a countable complement. Right? Well, what would that mean? Let's think about that. Well, that would be, this means the mu of x minus En star is 0. That's 0. Okay? And how do you show the other direction? Sorry, not the other case, right? The other case. And we never even use this 3 here. But, well, En is uncountable, right? So mu of En would be 3. Mu of En star would be 3. Would be 3. Okay, let me read chat, all right? So Steve says, notice that at most one of the En can be uncountable, right? So let's see why is that true. So here we have a sequence, E1, E2 all the way. That is a disjoint sequence. Okay. How can we see that? How can we justify the claim that at most one of the En can be uncountable? Right. Suppose let's say we have two uncountable members, EJ and EK. Right. K and J are not the same. Suppose that both are uncountable, and their complements are both countable. Right? X minus EJ and X minus EK are both countable. So you use the set identity, which is essentially the De Morgan's law. And earlier we assumed that EJ and EK are countable. So you use the De Morgan's law and say the complement of EJ intersect EK, which is the union of the complement of EJ union the complement of EK. That's countable. Yeah, that's countable. So what? So X EJ intersect EK is the complement of a countable set. If X is uncountable, EJ intersect EK cannot be empty. So EJ intersect EK should be empty. Yeah, so EJ intersect EK should be empty. And X minus, so that means EJ minus EK should be empty. So X minus EJ and X minus EK are disjoint. Is that right? The chat says, in chat says, if X is uncountable, EJ intersect EK cannot be empty. Why does that? Yeah, why does that prove at most 1? And actually, why is that even needed? Right? What we want this countable additivity. So suppose, let's say one of them is uncountable. Then the union would be uncountable. Right? So I think Steve is onto something. So the thing is, if let's say, think about what we want, right? I think Steve is onto something. The idea is, if you're trying to prove the identity for the second case, that is, if one of the En is uncountable, then the union would be uncountable. The union of En would be uncountable. So the left-hand side should be 3. To make this countable additivity true, this must mean exactly one of them has to be uncountable. Right? Let's say if let's say one of them is, if let's say 2 of them is uncountable. Yeah. I think you're onto something. I think you're onto something. So, 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 we want to show the right-hand side equals 3, which is suffices to show that exactly one of them is uncountable. We said at least one of them is uncountable. Right. We now let's claim that only one of them is uncountable. So let me just erase this part. Sorry. Yeah, it's countable. First of all, left-hand side is 3, since the union of En is uncountable now. Right. So need to show the right-hand side equals 3, i.e. Only En star is uncountable. And now I just need to prove it's impossible for two sequence members to be both uncountable. Yeah, after that it's easy, right? So suppose for a contradiction that another one is uncountable. Here only uncountable. Okay. By the assumption, since so suppose for a contradiction, yeah, I'm just trying to write your argument on my own. Suppose for a contradiction that there exists n prime not equal n star, such that En prime is also uncountable. By the definition of S, x minus En x minus En and x minus En star, En prime, are countable. And as a result, the union is countable. But by the De Morgan's law, so this is just x minus En intersect En prime. Actually, yeah, it should be star. My bad. Yeah, great job, Steve. This is amazing. Thank you so much. This is a fantastic argument. This is I credit you for this, actually. Thank you. Amazing stuff. Okay. So by the De Morgan's law, you got this set is countable, but since En star intersect En prime is empty, this means x is countable. On the other hand, En star is a subset of x, and En star is uncountable. So a countable set contains uncountable subset. That's impossible. Contradiction, and therefore we can't have another uncountable set in the sequence. So hence, exactly one member of E1, E2, and so on is uncountable. And therefore the right hand side, the sum of mu En n greater or equal to 1 is 3. There's only one of them is uncountable, so there's only one is 3. Alright, and that proves the statement. Okay, guys, this is fantastic stuff. Amazing. Love it. Okay, so we spend all this time doing verification of countable additivity, and actually this is usually the hardest part when it comes to constructing measures. So you define a measure you want to show is actually a measure. Showing countable additivity is typically pretty hard. Okay, so I think this is a good place to stop at Axler. So let's see what we let's do some ASH actually. I won't show the book because due to DMCA and stuff, but let's just start with just ASH's treatment. Okay, ASH's treatment. So we're trying to get into measure theoretic probability, right? That's what we're trying to do. Okay, so I'm just going to give the content, the list of content, just to see what we can expect. Okay, from ASH. ASH, because the meat and potato of ASH is actually a probability, and it does have some unique features. It does have some unique features as well. These are the list of content. Okay, let me just put in, there's a final page. We're gonna, and that's basically that's the layout of the book. Okay, so this is from Professor Ash's book, Robert Ash, fantastic writer. Rest in peace. He unfortunately died from a car accident when he was out for his walk, and he was hit by a car and unfortunately passed away. So yeah, Robert Ash, Professor Robert Ash, who used to work at University of Illinois, I believe. Professor Robert Ash, RIP. There was a link in the stream description on the passing of Professor Ash. So here in the book we have a rapid introduction to measure integration theory. Here in chapter 1, as you can see, we have field. It's called sigma field. Right? This is another terminology. Sigma algebra is often called sigma field. And we have the extensional measures. Extensional measures very much in the same line of thought as Axler. And measurable functions, integration, we already covered measurable function. Okay, and integration theorem. So this is roughly the same as the first 3 chapters in Axler. Here, chapter 2, we have some more important results, especially tailored for probability, actually. For example, here, 2.2, Radon-Nikodym theorem, which is a very difficult theorem. Radon-Nikodym theorem is used for example, defining the conditional distribution, conditional probability, conditional expectation. That's the Radon-Nikodym theorem. Extremely powerful in measure theory. It's only introduced near the end, in almost the end of Axler. I think this is going to be very helpful for us when it comes to doing probability. And also, so if you guys know a little bit about stochastic calculus, and also financial mathematics, there's this important concept called the change of measure, also known as Gersonov transformation. Also requires the notion of Radon-Nikodym theorem. Still, I promise to introduce the change of measure because it's so useful in option pricing. To a non-measure theoretic audience, I'm still trying to figure out, so to say, an accessible way to introduce it without actually formally introduce the Radon-Nikodym theorem, because that's a lot. But anyway, so we're going to do that in this series, of course. Yes. So basically, it's a derivative with respect to a measure. Right? Radon-Nikodym theorem is like the derivative of a measure with respect to another measure. So you can talk about things like density, but it's kind of abstract. Right? So, and here we're going to discuss LP spaces, very important stuff. A product measure and Fubini's theorem. This allows us to write a joint or a multi-dimensional integral as a double integral. Right? We use this technique all the time in regular calculus. But here's the general result: Fubini theorem. The Fubini theorem in regular calculus is rather limited, and it's a anyway, so this is useful, and in particular useful for independent random variables. Chapter 3, Introduction to Functional Analysis. Hilbert spaces, norm linear spaces, basic theorems on functional analysis. I wonder what they are. Probably like the open mapping theorem, Hahn-Banach theorem, something like that. 4. This is interesting. Interplay between measure theory and topology. I guess Fubini-Tolnelli is treated together. So Tolnelli, usually they're called Fubini and Tolnelli theorem, depending on the author, I believe. So chapter 4 is interplay between measure and topology. We'll see about that. Okay, we'll see if we actually need this. Now, Hahn-Banach is very important in functional analysis. The interplay between measure and topology. We'll see if we actually need this. Okay, but topic 4.2, the Daniell integral, is an alternative approach to Lebesgue theory. So in a Lebesgue theory, usually you define the measure first and then integration second. That's of course valid. You can also just start from the integration without talking about measures. So both have their advantages and disadvantages. Anyway, and 5 basic concepts of probability. So these are undergraduate probability from a measure theoretic point of view. Conditional probability, conditional probability. This is perhaps the most useful notion in all of statistics, because statistics is always some kind of conditioning, right? Given what, then what, then it's more likely what, right? Conditional expectation given a sigma field. This is actually one of the original contribution by Kolmogorov, is to define conditional distribution in a measure theoretic framework. And now you have classic probability, because at the end of the day, in probability, you usually wanted to prove some sort of asymptotics and that kind of thing. So this is actually one of the unique features of probability theory. Probability, generally speaking, but not always, okay? Generally speaking, interesting things happens when you have law of large numbers. N tends to infinity, sample size tends to infinity, okay? Usually, this is where a probability theory gets a lot more interesting. That doesn't mean in a small sample nothing interesting happens, but this is generally what we're trying to get to. strong law of large numbers and martingale theory, uniform integrability, and this is of course very useful for finance, martingale theory, central limit theorem, stable distributions, including uniform convergence in the central limit theorem, which is pretty cool. And at the end, you have an appendix on general topology. We'll see when we actually need this. Okay, so that's Ash's book, also very solid. Arguably, goes a little bit faster compared to Axler, but that's I mean, I've never used all of it actually, but I did have a good impression of it. It seems rather motivated actually. So and Robert Ash, I've read his other books, some of his other books. He was a prolific writer and over a diverse field. So and this one is well cited. So I have high hope for this one. Yeah, let's see. So skipping the summation, skipping the summary of notation section, which of course, if we run into trouble, we'll come back to that. And we're just going to start with chapter 1. Chapter 1 in Ash. It's called The Fundamentals of Measure and Integration Theory. Chapter 1 in Ash. Measure and integration. Fundamentals. Okay, so there's that. And it says from the very first chapter, it says from the very beginning that we don't assume a measure and integration. We'll give a self-contained presentation of basic concepts in the theory of measure and integration. The principles discussed here and in chapter 2 will serve as background for probability as well as harmonic analysis, linear space theory, and other areas of mathematics. Indeed, for example, PDE, the rigorous study of PDE, and even sometimes ODE needs measure theory. So it's a general skill. Okay, it underlies many topics. So starting from the first section, introduction, it will be convenient to start with a little practice of algebra of sets. This will serve as a refresher and also as a way of collecting a few results that will often be useful. Okay, nice. Just algebra of sets. So this is very much a warm-up. So let omega be a set. And you have A1, A2 are subsets of omega. Okay, so if we're going to define the limit of the sequence of sets, if say A1 is a subset of A2 and so on, and the union of an, n greater or equal to 1, is big A, we say that the sequence an is increasing. We say that the sequence an is increasing and with limit a. So this way we define the limit of an increasing sequence. Of course, not all sequences of sets are increasing. It's just a special case with limit a. Let's draw a diagram for that. This is big omega, right? And a1 is the smallest. This is a2. So you can think of this as this kind of infinite nested Russian dolls, and so on, right? So the union of all the ANs is big A. And just to remind ourselves, the union of AN, n greater or equal to 1, this simply means the collection of little omega in big omega such that there exists n equals 1, 2, and so on, so that omega is in AN. So this is nothing but the equivalent version of a existential quantified statement, existentially quantified statement, and statement with existential quantifier. It can be expressed alternatively as a union of sets. Okay, a notation for this behavior is as such. We write AN up arrow A. Okay, so that's the notation for the limit of an increasing sequence. So anyway, next up, similarly, you got the other direction. If A1 contains A2, contains and so on, and the intersection of AN, n greater or equal to 1, is A, we say that the sequence AN is decreasing with limit A. With limit A. Of course, the notation, as we can imagine, goes like this. So AN decreases to A. And this is a diagram. Omega. A1 is now the biggest set. A2 is smaller. And it goes like this. Okay? So AN decreases and converges or with limit A. Right? So that's the second version. Of course, you can use the De Morgan's law. By the De Morgan's law, you have these simple properties. By the De Morgan's law, yeah, for example, AN exactly. Let's just give an example. It's a great example given by Steve. Thank you very much. So let's say AN is 1 over n 1. Is this increasing or decreasing? Let's draw the picture. Consider them as subsets of R. Okay. So when n equals 1, that's empty. Yeah, that's fine. You can take empty set as sequence member. That's totally okay. When n equals 2, that's 1/2 to 1, right? That's A2. And then as n gets greater, the left endpoint approaches 0. This is 1/3. So this is A here. This is A2, and this is A3, like this. So it's clear that the sequence AN is increasing. And what's its limit? AN would increase to 0 to 1. The open interval 0 to 1. So this is an example. Okay, cool. Awesome. Thanks a lot. Thanks a lot for the example. By the De Morgan's law, that is the union. Let's just write the union n greater or equal to 1 a n complement. Okay, I'm going to use this notation for complement. This is the intersection, n goes from n greater or equal to 1 a n complement. And also the other way around, the intersection of n greater or equal to 1 a n complement is, is the union n greater or equal to 1 a n c. This is De Morgan's law. So by the De Morgan's law, we have the properties. We have the following properties. So, 1, okay, if an increasing and has limit a, then ANC is decreasing and has limit AC. Right? This is very intuitive. This is very intuitive. Let's try to prove it. Okay. So first of all, this is a little proof. So assume the hypothesis. So AN goes to A. Okay, by definition, A1 is contained in A2, and so on. And the union of AN n greater or equal to 1 is A. Okay, then, well, because of the containment relation, A1C contains A2C contains dot dot dot, and the intersection of A and C, n greater or equal to 1, is AC. And therefore, by definition, A and C is decreasing, which converges to AC. Okay, it's a very simple proposition. Okay. Second, well, it will be the other direction, so I'll skip the proof. If AN decreases to A, then A and C converges, it's increasing and converges to AC. Right, proof would be similar to 1. So we'll skip that. Okay. And we can rewrite an arbitrary union as a disjoint union. We can always do that. So here, let A1, A2, blah, 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 be in as subsets of omega. The point is here, write a union as disjoint union. Any countable union as disjoint union. So this is a useful thing because we've seen in Axler that we want to talk about countable additivity, right? And there we require, hang on a second, why is this so huge? Okay, anyway, this is fine. So how can we write the union of n greater or equal to 1 as a countable union? Let's draw a picture here. I just need a few to get the idea going. So this is, say, A1. So it might overlap with A2 like this, and it might overlap with A3. So in general, the relationship between the members can be very complicated. right? So how do we go about writing this as a countable union? Well, we can say first we're just going to pick the whole of A1. Just take everything in A1 as our first term, if you will, in the countable union, disjoint union. So this is just A1, and union with what? Well, because we want disjoint union, everything in A1 cannot be included from now on. So let's just do A2 minus A1. This is by definition by definition has no overlap with A1. Let's draw an image for that. So this is a part that we want here. I think we've also seen this in Axler. So here you go, that's our second term, A2 minus A1. And what will be the second? What will be the third, actually? So you can think of as A3 minus A1 and A2. Right? That makes sense? So that would be A3 minus the union of A1 and A2. A3 minus the union of A1 and A2, like this. And just keeps on going. Okay, let me highlight the last region here. So this is perhaps a natural way to construct or rewrite any countable union as a disjoint union. Okay, and of course you can rewrite the set difference in a different way, in another way, equivalent way. So A1 union with let's write that as A1C intersect with A2. This is the same as the set difference. Okay, and the third term, A3 minus the two thing, okay, would be what? Well, you need A3 in there, and you don't want A1, you don't want A2. So it would be A1C intersect A2C, and then intersect A3. And that's an equivalent way of writing the previous construction. Okay. And what would be the general term here? The general term would be you have A1C intersect all the way to AM minus 1C and then intersect AN. This is the nth term, and then you keep on with the union. So this way you can write any countable union as a disjoint union. Okay, so this is a nice thing to have. So let's write it as this notation. Say this is the union n from 1 to infinity. A1C intersect all the way to AM minus 1C intersect AN. Okay. Okay, so there's that. Okay. So this is rather general, but let's say if you have special cases that the AN is increasing. If AN is increasing, this can be simplified. Now, take a look at the picture. If AN is increasing, like this, A1, A2, and so on, and because of the nested structure, the first term is A1, the second term would just be A2 minus A1, and then the third term would be A3 minus A2. So that's a special case. If AN form an increasing sequence, many times you will see the disjoint union symbol as a union symbol with a square bottom. Yes, yes. Yes, you're totally right. And sometimes I see this. There's a plus sign in the middle. And sometimes you simply see disjoint union as a big sigma. Okay, yeah. To emphasize this is disjoint union. If AN form an increasing sequence, then the union of AN, n from 1 to infinity, this is simply A1 a union with A2 minus A1. So sometimes I write the set union this way, and sometimes I write it. Actually, that's not a good idea. Actually, let me just unify the notation. Okay, this is set difference. I think Baby Rudin uses the minus sign here. Baby Rudin use the regular minus sign for set difference, even though nowadays it's more common to write set difference this way. Okay. Anyway, so yeah, this is A3 minus A2, and the pattern keeps on going. Okay. So yeah, this is for increasing sequence. And now we're going to we're not going, and yeah, sometimes you see backslash. Yeah, sometimes you do. And now we're going to define something. Actually, it's going to be very useful. It's called the upper and lower limit, or also known as what we call the lim sup and lim inf. The upper and lower limits. We actually give an exposition earlier in Axler. I mean, Axler did not use those, but in an attempt to understand a proof, I briefly reviewed lim sup and lim inf, and actually that was which day? No, this is exercise, perhaps earlier. The 23rd, huh? 23rd is also exercise. Oh, actually, yeah, here. On the 23rd, if you go to 23rd, I did a brief review of lim sup and lim inf in R, and then define lim sup and lim inf for sets. Okay, and prove the properties that lim sup consists of is also known as so-called AN infinitely often, and lim inf is called all but finitely often. Okay, so yeah, I'm just gonna do it again. Okay, just do it again. So that's okay to make the presentation more self-contained, and it's in my experience somewhat of a tricky notion. Perhaps it has to do with the fact that the lim sup and lim inf are not very often practiced. It's just a matter of frequency of practice. Because in classical analysis, limit is usually defined in terms of the epsilon big N definition. Nothing wrong with that. In classical analysis, that's typically the overwhelming approach, overwhelmingly common approach is to use epsilon big N. But the thing is, you need a metric structure. You need a notion of a distance to define limits. Big N, big epsilon big N way. But the problem is, if you're dealing with sequence of sets, what kind of metric should you use? There's no natural choice. There's no canonical choice. Right? So the next possibility is to make use of the order structure. Here, for subsets of a big set omega, you have a natural order structure, which is containment. And you can exploit that to define what we call the limit in a general situation. And this is how it's done. So this is what we're going to define next. Okay, so so let A1, A2, and so on be subsets of big omega. They don't have to be increasing or decreasing. Okay, just a general sequence. Let me just draw the picture here. Venn diagram. Okay, omega is A1, A2, A3, and so on. It can be very general. And so we're going to define the lim sup and lim inf as follows, and we'll try to make sense out of the definition. So the lim sup of an is defined as the intersection of n from 1 to infinity and the union k from n to infinity, ak. And the next definition is the lim inf. The lim inf of an is defined as follows. So you flip the operation going from intersection to union, and k from n to infinity, ak. Yes, exactly. So that's the two very common notion that will show up a lot in probability, and they have probabilistic interpretations. But let's just try to think about what do they mean. Okay, why are they constructed in this weird manner? So this is the intuition here. So this is the intuition. So so if we take, say, Bn, define Bn as the union of k from n to infinity, ak. This is a sequence labeled by n. So Bn, the point is Bn is decreasing. Can you think of why? Because as n increases, the number of sets, ak, that take part in the union decreases. So imagine this is your sequence, right? A1, A2, A3. B1 is the union of all of them. B2 is the union of A2, A3, and so on. And B3 is the union of A3, A4, and so on. So the larger the n, the fewer the sets, or the more sets are excluded. The more sets, AK, are excluded from taking part in the union. So Bn decreases. And what about, say, what about the hang on. So what I'm trying to say is, so Bn decreases. Yeah. Yeah, Bn decreases. And also, what about the intersection? Intersection of AK. So k goes from n to infinity. And let's call that Cn, all right? And Cn would increase for exactly the same reason earlier. So when n equals 1, C1 is the intersection of all of AKs. A1, A2, A3, all of them take an intersection. And C2 is the intersection of A2, A3, and so on. The A1 is now excluded. When taking intersection, the fewer the sets in the operation, involved in the operation, the bigger the intersection. Because taking intersection will always result in a smaller set. So when n gets larger, you have fewer sets taking part in the intersection, so Cn goes up. So that's the observation here. And now, well, what's the limit of Bn? If Bn is decreasing, then the limit of Bn earlier, if Bn is decreasing, the intersection will give you the limit. So that's why you have an intersection here. Is the limit of Bn is the intersection of Bn, n greater or equal to 1. All right. So
the limit of Cn, because it's increasing, then you would take the union and goes from 1 to Cn. Okay? So why does it, I mean, it makes sense that these two expressions on the right-hand side have limits, right? The limits are well defined, but why are they called lim sup and lim inf? Well, you can think of this notation as defined as follows. So lim sup and lim inf n, okay, are really just shorthand for the following. Okay, lim sup n an, okay, this is a shorthand for the limit n goes to infinity, the supremum of ak k greater or equal to n. So this is our Bn. This is our Bn. So why this can be considered the supremum? Because Bn is greater or equal to, or well, should be contained. So you can think of containment as some kind of inequality sign. So Bn is greater or equal to, because it's the union of all the AKs, right? So there is greater or equal to all the AKs for k greater or equal to n. And the intersection, on the other hand, is less than or equal to ak. So that's the infimum. So this is the analogy that you draw from real analysis. Okay, so the lim inf, once again, is a shorthand of n tends to infinity taking the limit, and then the infimum. Yeah, the expression seems complicated. The idea is really simple. So is an idea of bound squeezing. It's an idea of a bound squeezing. So once again, why don't we just take an analogy back to in real numbers? In the real numbers, this is analogous from the real numbers. So let's say analogy from real numbers. Actually, I've drawn a picture earlier. Let me just import that, all right? So yeah, this was the analogy from the real numbers. So here, I won't redraw it again. Just see this picture. So the black dots represent points of a sequence in the real numbers, and it might not converge. But for the sake of argument, let's assume this is bounded. Let's assume this is bounded, and now let's consider the quote-unquote n's tail. The n's tail of the sequence. The n's tail of the sequence consists of, well, elements that start from, or say, case tail. The case tail of the sequence an consists of ak plus 1, ak plus 2, and so on. So it's now start from ak now. This is a case tail. Okay, so we're interested in the supremum and infimum of the case tail. As n increases, the case tail as a set decreases. As a tail, I mean, because as k increases, the tail as a set decreases. So its supremum becomes smaller and its infimum becomes larger. And this is what happened. So the green upper bound here tells us the behavior. The green upper bound up here tells us the behavior of the sup of the tail. Okay, this is not T1, but rather Tk, n greater or equal to k. Okay, so where are we? Here. Tk. Okay. So the point is, we're squeezing the bounds. If we look at the case tail, its supremum is a decreasing sequence, and its lower bound is increasing sequence. And by the property of real numbers, monotone sequence must converge. So the limit of the soup of the case tail decreases and is bounded and must have a limit. That's the lim soup. Literally the limit of the soup. Limit of the soup. Soup of what? Soup of the case tail. And lim inf is defined similarly because the infimum of the case tail is increasing. So we're essentially squeezing between bounds. And this is actually the same idea that we define the Riemann integral, or more appropriately, Darboux integral. Is also squeeze bound. So in here, let me just do a brief review of chapter 1. When we define the Riemann integral, we first define the notion of upper and lower sum. Upper and lower sum. Okay, this is the image. You could do the partition. In the upper sum, you take the maximum over each interval times the interval length and you sum it up. Right? This is the upper sum and this is the lower sum. Of course, the upper sum is always greater than the lower sum. That's for sure. For any given partition, the upper sum is greater than the lower sum. That's trivial. But the idea is, if you refine your partition P, let's put more and more discrete points in there, put more and more subintervals in P, the upper sum decreases and the lower sum increases. Always. As P gets more refined, the upper sum always decreases and the lower sum increases. So you're squeezing the bound. The true integral is between the upper sum and lower sum. And now you're making the lower sum bigger and the upper sum smaller, exactly like in this picture. So this is a bound squeezing idea. It only requires an order structure. It does not require metric structure. That's why it can be imported almost verbatim to set, because there's a natural order between sets. All right, analogy from real number. So this is how the lim sup and lim inf are defined. All right, so and we're going to show a few facts. Okay, I'm going to show a few facts. So that is to say, hang on. Facts, properties. Omega belongs to the lim sup of an if and only if we call omega belongs to an infinitely often. And sometimes we just write ANIO in probability. Okay, so this is a fact. Let's see the proof of it. So well, which number we're looking at? 1, 2. Okay, let's call this 3. Okay. Proof. So omega belongs to the lim sup of an, which by definition here is the intersection n from 1 to infinity. Right. And once again, there's a nice way to memorize the order. Remember how we said that the sup of an is decreasing. The sup of an, the sup of ak as k greater or equal to n, as a sequence labeled in n, is decreasing. So to get the limit of a decreasing sequence, you take the intersection. Right? So intersection goes first, and now you just need to know the other symbol is reversed. So there you go. So that's the lim sup. All right. This happens if and only if omega is there exists, right? Actually, for all, because this belongs to the intersection, so it's for all n equals 1 and 2 and so on. Right? This is just basic skills that we mentioned in the what we call the basic skill we mentioned in the introduction to proof writing live, because you can think of it as a bridge course from regular calculus, non-proof based calculus, to more rigorous text on real analysis, probability, differential equations, and whatnot. Okay. So yeah, the proof session we did last week, that's not the only session. Okay, we'll continue on that. Can be considered a bridge course on more advanced or more proof-heavy mathematics. I call it the Introduction to Proof for Applied Scientists, in a sense that you just need to be literate when it comes to reading mathematical literature, and you don't necessarily need to prove theorem yourselves. Okay, I just want applied scientists to be able to follow a mathematical proof, right? And to prove a theorem, what is needed to be done, okay? And not so much emphasis placed on the ingenuity involved when it comes to constructing sophisticated proofs. Guys, I'll use the bathroom. I'll be back in 1 minute. All right, I'm back. So here, just let's prove this statement. The interpretation of lim sup. This is super useful probabilistically because an in probability are events. These are events. Omega is what we call the sample space. An is an event, right? So you have a sequence of events, and this is quite usually what we're interested in. If you for example, in the study of Markov chain, there's this notion of recurrence. A Markov chain revisiting the same state over and over infinitely many times. So this is a very useful formalization of that idea. So omega in the lim sup, let's just unpack the definition, okay? So omega is in its infinite intersection. That means for all n, okay, for all n equals 1, 2, and so on, omega is in the union of k from n to infinity ak. And this just means that for every n equals 1, 2, and so on, right, because this is an infinite union, this just means there exists a k that's in the range n plus 1, and so on. Omega is in a k. Okay, let's think about what that means. Right, let's think about what that means. So, here, you have for every n equals 1, 2, and so on, there exists a k. There exists a k greater or equal to n. Because k is greater or equal to n, these k's, they form a subsequence. Let's call this k, called kn. Let's call it kn. And let's denote this k called kn. For each n, there is this kn. And here, this is the same as omega belongs to akn for all n. And where akn is a subsequence. Of course, when you talk about subsequence, there are infinitely many members of it. Right? A subsequence, by definition, is a sequence. So, yeah, there's infinitely many of them. Omega in an infinitely often. So we're done. Now, it's a rather simple proof, just to unpack the notation of the set theory as well as quantifiers. All right, 4. Lim-inf also has a nice interpretation. It says if, let's say, omega is in the lim-inf of an, this means omega is in an eventually. Aka omega is in an for all but finitely many n. I.e., let's see how that works. So it's like it will reach when the index n reach a certain stage, reach a certain threshold. Every set after that index will contain omega. So omega in an eventually. So that's the interpretation, probabilistic interpretation. And that's pretty cool. Lim sup corresponds to infinitely often, and lim inf is eventually. It's always there. Eventually. It's always in every single set, or equivalently saying omega is in an for all but finitely many. You can only not belong to an for finitely many n. That's the idea. Okay, proof. Omega in the lim-inf of an. Oh, by the way, there's also the alternative notation. Which is also pretty common. Perhaps nowadays in older text. Okay, lim sup is written as lim with an upper bar on top, and lim-inf is written as limit with a lower bar at the bottom. This is also pretty common. Okay, just want to mention that in passing. Omega in the lim-inf, which is what? Let's not look at the definition. Let's think about how this works. It is literally the limit of the infimum of the tail. Right? Infimum of the tail is increasing, so its limit is a union. And then the tail would use n greater or equal to k, ak, 1 to infinity. All right, so that's the definition of limit inferior. And when this happens, this means there exists an n equals 1, 2, and so on, such that omega is in the intersection of n greater or equal to k, ak. Well, what does that mean? It means there exists n equals 1, 2, and so on for every, right, literally for every k equals n plus 1 and so on, omega is in ak. And that's exactly the idea of, oh no, oh no, something is wrong here. Guys, my screen went dark. My screen went dark. Okay. Is it better now? Okay. Now I should be back. Yeah, video is off. Yeah, because the power
got disconnected. Okay, so is it better now? Yeah, it went off for a second and now it yeah. Let me know in the chat. Okay, great, awesome. And as you can see, this is literally saying that omega is in a k for all in a k eventually. Yeah, there exists a threshold such that passing that threshold means every AK contains omega. Okay, thanks guys. Right. So also very straightforward. Okay, and now let's just to give a more facts. For 5, this is the lim sup of an complement is the lim inf of a and c. Okay, and the proof I believe is just an application of the De Morgan's law. So the left hand side is the lim sup would be the intersection n from 1 to infinity, a union n greater or equal to k, a k, taking the intersection, sorry, taking the complement, in which case you flip it, it goes from n from 1 to infinity, n greater or equal to k, a k quantity complement, and then it becomes n from 1 to infinity, intersection k, n greater or equal to k, a k, c, which is exactly the lim inf of a n c. So which is the right hand side. Okay, so we're done. And 6 is the lim inf an quantity taken complement is the lim sup of a and c, and the proof is similar to above. Still, De Morgan. Just use De Morgan. So I'm not going to prove this one. 7, it says the limit inferior of an is a subset of limit superior of an. And this is obvious based on their interpretation, right? Because if omega is in an, eventually it appears in an infinitely often. So that's trivial. So just say omega appears, or should we say omega in an eventually implies omega in an infinitely often, and that's just the end of the proof. Okay, and and lastly, we want to show that, say if let's say if an goes up, if an goes up to a, or an comes down to a, okay, then in both cases the lim sup and lim inf would be identical. Would be identical, and they're both a. Okay, so let's prove that. Let's do the first one. So let's assume an goes up to a,
Okay, let's think about what this means. Then by definition, AN is increasing, so A1 is a subset of A2 and so on. Okay, and the union of AN is A. That's what we have. So you need to show both the lim sup and lim inf in this case is AN. All right. So let's try that. The lim sup of AN by definition is the intersection n from 1 to infinity union n greater or equal to k, ak. Okay, all right. So what is this thing then? What is this thing? This is the union of ak when n is greater or equal to k. N is greater or equal to when hang on, is that right? The union of ak. Actually, k greater or equal to n. That's not right. Maybe I made the same mistakes earlier. Yeah, I think I made the same mistakes earlier. This is a finite union. This is not right. Okay. That's actually quite a significant mistake. And k should be greater than n, not n greater than k. Okay, so this is still an infinite union. Yeah, no worries. Yeah, Steve, thanks very much for hanging out this long. I'm gonna do another half an hour and call it a day, and we'll continue. Actually, tomorrow morning there will be a stream. Actually, you know what? Yeah, I think I'll do a half an hour. I promised 5 hours, but I'm getting a little bit tired as well. I had a full day. So tomorrow morning I'll do, upon request, I'll do a limit and continuity, good old calculus, good old introduction to analysis, whatever you want to call it, stream from a classic Russian text called Mathematical Analysis by Zorich. So hopefully, yeah, we'll have some fun there too. Anyway, so here, just fix that mistakes, those mistakes. So it should be k greater or equal to n. Okay, there's no need to memorize this by brute force. Now, both the intersection and the union involved are infinite. Okay, so here, let's think about what's happening here. Okay, this is what. This is what here the union of AK. The union of AK, where k is greater or equal to n. I would argue that's just the union of all the AKs, not just k greater or equal to n. Think about why. Let's draw a picture right next to it. So it's always a nice idea to pair this with a Venn diagram. So A1 is the smallest, all right? A2 contains A1, like such. Right. And dot dot dot, this is AN, and keep on going. Right. Because this is increasing, this union right here, even though it only started from AN, it contains everything before AN. So this is really just the intersection of n from 1 to infinity, the union of AK, k greater or equal to 1. So this is just A. So you have an intersection of identical sets, which is just A. From the picture. Okay, now what would be the limit inferior, lim inf of an. The lim inf of an would be the union n from 1 to infinity. The intersection, k go from greater or equal to n, ak. And what would that be? Let's think about what's happening here. Well, here, because you're taking the intersection of ak, k greater or equal to n. And look at the picture. Let's say if n is 1, right? The intersection of a1, a2, and so on. Because a1 is the smallest, then all of them, then if n is 1, then this intersection is just a1. And if n equals 2, the intersection is a2. So this is just here. Yeah, this is just an. Once again, because of monotonicity. So this is just the union of an, which is by the assumption a. Okay? And now let's do the other scenario where an is decreasing. If an is decreasing and goes to a, so in that case, you have this situation, a1 contains a2, contains and so on. And the intersection of n greater or equal to 1, is a. So it looks like this. Okay, so draw the picture. A1 is the biggest, A2 smaller, and so on. This is AN. It keeps on going, right? So that's the situation here. Let's evaluate the lim sup. What is the lim sup of AN? By definition, that's the intersection. And from 1 to infinity, taking the union, k greater or equal to n, ak. And see how do things work. So this union is the union of an plus 1, an plus 3, and so on. But because an is greater than an plus 1 and an plus 2 and whatnot. So this is just an. Because of decreasing, the union is just an. And of course, this is just a. Right, that's the lim sup. What about the lim inf? Well, the lim inf of an is the union n from 1 to infinity. Intersection k goes greater or equal to k greater or equal to n, ak. And what's that? What is the intersection of all the AKs? Let's think about it. What is the intersection of all the AKs, k greater or equal to n? Hang on a second, is that right? The intersection, yeah, here because of the you're taking the intersection of all the say, for example, let's say n equals 1. If n equals 1, that's the intersection of all the AKs, right? K from 1, 2, and so on. That intersection is just a. This is always a. This is always a. So that's just the union of a constant, which is a. So we're done. Okay, so that's the property 8. Okay. And finally, we give the definition for a general sequence. It doesn't have to be disjoint or increasing or decreasing. A1, A2, all the way in is a subset of omega, not in omega, but rather a subset of omega. For general sequence, okay, if the lim sup of an equals the lim inf of an equals a, we say that the limit of an is a, right? And this is exactly the same definition of limit in the context of sequence of real numbers. You can define the limit of a sequence of real numbers not through epsilon big N, but rather through lim sup lim inf. And lim sup lim inf only requires the order structure of the real line, which we literally borrowed almost verbatim in the context of sets, right? Because on a set you still have this natural order relation, but not so much of a metric structure. So this is the definition. If the lim sup and lim inf agree, then we say the limit of an is a. So that's the definition of the limit of a sequence of sets or events later on. Okay, so that's a very useful definition. Okay. Okay, let's do more examples. In this case, this would be example, okay, rather than general proofs. Let's do a problems. Problem. So, this is a concrete calculation. Problem 1. Say, let an be the set of real numbers, open endpoint -1 over n to 1. Okay, and so let me just write it this way. Okay, when n is even, actually when n is odd, my bad. The other scenario is as follows. So it's -1, 1 over n. And it's open and closed like this. So here you have two cases, okay? If n is odd, then an is the interval -1 over n to 1. Left endpoint open, right endpoint closed. And if n is even, an is -1 to 1 over n. Left open, right closed. All right, so that's the definition of an. And we're asked to calculate, okay, the lim sup of an and the lim inf of an. It's an interesting exercise. Let's see how that's done. First of all, why don't we draw a picture? Because this is rather concrete. Here you have 1 at the right endpoint when n is odd, right? So this is 1, and -1 over n is always less than 0. Okay, when n equals 1, that's a -1, like this. So let's highlight this. This is A1. Let's put a solid dot here to indicate 1 is always included. Okay, so this is A1. So when n is 2, actually let me go n equals 3. Okay, still n odd. In that case, you got -1 over 3, and this set is A3. And it's 3. Okay, and as n gets larger and larger, -1 over n approaches 0 from the left, like this. Okay, so this is 0. So these are the ANs when n is odd. Look at another situation where n is even. Okay, when n is even, just label it down here. Okay, label it down here. So when n is even, so n equals 1/2. Starting from, sorry, n equals 2. N equals 2. That's the first even case. When n equals 2, it goes from -1 open interval, open endpoint, to 1/2, which is closed, like this. 1/2, and this is A2. Interesting. And then the next even number would be 4, and point would be 1/4. Okay, so this is A4, like this. Okay. So first of all, we notice that it is not a nested sequence. Okay, it is not increasing or decreasing. It's not a monotone sequence of set. It's not. It's not a monotone sequence of set at all, right? So for example, A3 and A2 are neither contained or is contained by one another. So this is not a monotone sequence. To find the limit superior, what do we do? Let's apply the definition. Okay, let's apply the definition. First, the limit superior of an by definition is the intersection n from 1 to infinity, the union n greater or actually k greater or equal to 1, k greater or equal to n, ak, like this. Okay, so as I was saying, this is like the supremum, right? This is the supremum of ak. But how do we evaluate it? Can we evaluate this part first? Huh? That's our goal. Fix n. Okay, fix n. Can we find the union of ak, k greater or equal to n? Can we do that? You have to kind of guess the answer from the picture and then show this rigorously. So if we fix n, and we're taking the union of all of them, so let's do some explorations. This way, perhaps it's more clear. It should be noted that the even case covers all the positives from 0 to 1, including 0. And the sorry, my bad. The odd cases covers everything positive in 0 to 1, including 0 and the point 1. Whereas in the even case, it covers all the negatives, including 0, but not 1, but not minus 1. But not minus 1. So something to bear in mind of. It's something to bear in mind of. All right. So when we take the union of ak, k greater or equal to n, of course, this would include AKs where k is both even and odd. I think that would just covers everything, huh? Everything from -1 to 1. -1 open and 1 closed. What do you guys think? I think, yeah, it should be just, this is just -1 to 1. It's really simple. Say, let's look at some special example. Say, if we let n equals 1, the union of a1, a2, a3, and so on, everything that comes after a1. Well, a1 is just -1 and 1. And everything else is a subset of a1, so just -1 and 1. No problem. So starting from 2, what happened? You got a union a2, a3, a4, and so on. So a2 and a3, already covers -1 to 1. The idea is all the even integers, all the even cases covers the negative, and all the odd cases cover the positive. So just -1 to 1, and of course intersection, which is trivial, which is -1 to 1. Okay, that's our first observation, and we need to prove it. Okay, and we need to prove it. So let's actually just do the proof right now. Right. So basically, we want to prove this part. So, as I was saying, it suffices to show for all n equals 1, 2, and so on, the union of AK, k greater or equal to n. Actually, this is actually a great exercise for my intro to proof theories, because it assumes almost nothing, right? And it's a good way to exploit how do you approach a proof. Okay, how do you first guess the result and then prove it. So really, it has nothing to do with measure theory, but it's a good exercise for just proof writing in general. And I think actually that's the greatest prerequisite for measure theory, just the ability to read statements and to read proofs and to write proofs. You don't need to know all the trickeries, right? Learning the trickery is part of learning measure theory, regardless how much prior experience you have. Right? It has, I mean, of course, individual real analysis result can be taught as a need-to-know basis, but the most important skill is actually just to read the statement and just do proofs in general. Okay? No domain knowledge is particularly so to say called for until when you actually reach them. Anyway, so here I was saying, like, I digressed. Okay, so this is, I want to show this is -1 to 1. -1 to 1, like this. Okay. To do this, we can simply pick, say, a proof technique like contradictions, etc. over. No, not at all. It's important. Super important. What are you talking about? Kraken. Contradiction, contrapositive are super important. They're called indirect proofs, and they're lifesavers. I mean, we use the proof by contradiction today. Remember the argument given by Steve. It was such a brilliant argument, right? Suppose for a contradiction, we want to show that in the last accelerators example, in a sequence En, there's only one uncountable. There's a contradiction argument. What do you mean? Like, contradiction is super important. And earlier in a part of the chapter 2, we proved that there is no reasonable extension of length for all subsets of R. Once again, contradiction. That is to say, the axioms of the proposed axiom for the extension is mutually contradictory, which is the whole reason why measure theory is needed, why sigma algebra is needed, and all those shenanigans, right? So, extremely important, extremely powerful, okay? And without contradiction, I mean, well, you might be an intuitionist or constructivist. Contradictions are a very powerful method. Must be mastered. Okay, so anyway, here I was saying, like, just based on the picture, I would like to argue that the consecutive elements, so you start from AK, AN, and so if n is even, let's just do it this way. Okay, if an is even, then an is what? From the picture, is minus 1 over n. to 1. Right? And what is an plus 1? An plus 1, that's an odd case. And oh, my bad. An is even. Sure, let's start with an odd. If n is odd, an is minus 1 over n to 1. And an plus 1, that's even. Again, minus 1 to 1 over n plus 1. Like that. Right? So this way, the union of k greater or equal to n, ak, of course this will contain the union of just two sets, an and an plus 1. And what's the union of the two? The union of 2 is just minus 1 to 1. Okay, and the other case, if n is even, to the other case, an is what? Is minus 1 to 1 over n, and an plus 1, that will be, n plus 1 is minus 1 over n plus 1 adds to 1. In that case, same idea. The union of ak, k greater or equal to n, contains an union ak, an plus 1, and covers the negative, n plus 1 covers the positive, so you get minus 1 to 1. So regardless, the left-hand side contains the right-hand side, like this, and you need to show the right-hand side also is contained in the left-hand side. Okay. All right, so, well, isn't that the same idea? Isn't that the same idea? But let's say, just say, okay, let x be in, let x be in the union of ak, k greater or equal to n, x be in the union, okay? All right, so once again, let's consider two cases. So when x is less than or equal to 0, so to say, when xn is less than or equal to 0, so that means x is in the second scenario. So here, x is in here. I mean, fix n. Okay, fix n. When x is less than or equal to 0, that means x is here. Can I say, yeah, this is already less than or equal to 1 over n. Yeah, just by the transitivity of inequality. Okay. And this means x is in minus 1. Is in minus 1 to 1 over n. We don't know whether this n is even or odd, but what I'm saying is you can make this even. You can make this even. Just pick an n star. Okay. Just pick a k that is even, that is greater or equal to n. Okay. Let me write it this way. X is less than or equal to k. For k greater or equal to n, k greater or equal to n, and k is even. I mean, if x is less than or equal to k, it is always less than or equal to 1 over k. And we're just going to pick the k that is greater or equal to n, and k is even. So this way you get, okay, x is in -1 to 1 over k, and that's what? That's ak. And that's ak, which is contained in the union of ak k greater or equal to n. So that's the first case. In the second case, let's do when x is positive. When x is positive, then x is greater than what? X is greater than -1 over k here, where k is greater or equal to n, k ought. This way x is in the interval -1 over k to 1, which is ak, which is a subset of union k greater or equal to n, ak. That finishes the proof. So together, therefore x is always in. Hang on a second. Oh, my bad. My bad. This is not what I wanted. I want to show this is on the right. This is, guys. I'm getting too tired. So, but basically, this is in -1 to 1. Also in -1 to 1. Okay. So overall, the identity is proved. So that's the limit superior. I'll finish the limit inferior and we'll call it a day. So this finishes the proof. All right, limit inferior. What's the limit inferior? So first let's still explore and then make the conjecture and then prove it. Limit inferior of an, by definition, is the union n from 1 to infinity intersection k greater or equal to n, ak. What would that be? What would that be? So think about the intersection. Intersection is a bit tricky here. You want to find the common region, so to say, of ak, k greater or equal to n. And that seems to be only 0. That seems to be only 0. Think about it. So even in this diagram, so the intersection of A1, A2, A3, A4 would be what? Would be in the middle area. Would be from -1/3 to 1/4. And as n tends to infinity, all that's left is just the middle, it's just the center, it's just 0. So it's just the union of 1 to infinity, 0. And we will be done. So yeah, so to show this, it suffices to show for every n equals 1, 2, and so on, the intersection of a k greater or equal to n is just the set 0, the singleton. Of course, 0 belongs to all of them, so this direction is trivial. This is obvious. Right? Because each ak contains, all the ak's contain 0. So that's obvious. So let's do the other direction. So let x be in the intersection of ak, k greater or equal to n. Okay, once again, fix n. So what does that mean? So what does that mean? Well, let's do two cases, shall we? So case when n is even, x is in the A case where k's are all the k's are all even. So let's this would be an starting from an, right? M plus 2, m plus 4, and whatnot. Right. So in that case, when n is even, this tells us that when n is even, that means x is less than or equal to 1 over n. X is less than or equal to 1 over n. X is less than or equal to 1 over n plus 2. X is less than or equal to 1 over n plus 4, and so on. And also, x would be in am plus 1, am plus 3, am plus 5, and so on. What would that mean? Well, look at the odd case. It would be greater than an would be x would be greater than 1 over m plus minus 1 over m plus 1, x greater than minus 1 over m plus 3, x would be greater than minus 1 over m plus 5, and so on. And therefore x is 0. The only number x that satisfies all these inequalities is 0. Okay. The next case, n is odd. When n is odd, well, it's pretty much the same business. So x would be in an plus 2, an plus 4. These are all odd numbers. Okay, this would mean x is greater than 1 over n, x is greater than minus 1 over n plus 2, x is greater than minus 1 over n plus 4, and so on. And x is also, x is in am plus 1, am plus 3, am plus 5, which means x is less than or equal to 1 over m plus 1, x is less than or equal to 1 over m plus 3, x is less than or equal to 1 over m plus 5, and once again, the only possibility is x equals 0. So we're done. Alright guys, thank you very much for watching. This has been an amazing stream, and yeah, we'll continue next time. I'll continue the study of measure theory, probability, all of that next time. And so yeah, and as promised, next week we'll see a revival of the stochastic stuff on the channel. In particular, we'll introduce what physicists care about and what perhaps quant cared about, and we'll see what to do from there. Okay. And tomorrow morning there will be a session on limit and continuity, classic analysis, upon request by Vladimir Zorich. Okay, that will be it for today. Thank you guys very much for watching, and I'll see you guys